hits the ground, I turn around, you know it was only a dream. 'Cause nothing is as bad as you think, even when you're pulling at the seams. When the lights go out, you still got me. Oh, 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 oh. Detours lead to barricades, and home is for your friends are fake. I'll be there to clear the way. Oh, 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 oh. And you know my love can hold you down. You know my love can hold you down. And you know my love can hold you down. You know my love can hold you down.
Sneha madam, I think we can start.
Yes,
madam.
sir.
Yes, sir. The capacity to learn is a gift. The ability to learn is a skill. The willingness to learn is a choice. Well said by Brain Hobart. So, on this vibrant morning, we are happy that all like minded people willing to learn by their choice have gathered here. Very good morning to everyone present here. I, Priya Deshpande, welcome you all on behalf of Organizing Committee, Electronics Engineering Department of Bharatiya Vidya Bhavan's Sardar Patel Institute of Technology. It gives me immense pleasure to welcome our delegates, our own principal, Dr. B.N. Chaudhary, Program Evaluation Committee members, Dr. D.C. Karia, Head of Electronics Engineering Department, Dr. Reena Sonkusri, Head of Electronics and Telecommunication Department, Dr. Sukanya Kulkarni, Associate Professor at Electronics and Telecommunication Engineering Department, today's guest of honor, Mr. Anirudh Satoskar, Design Engineer at Cirrus Logic, USA, Dr. Muhammad Hassan, Professor at AMU, all teaching, non-teaching staff, and all participants. I welcome you all for 1 week AICT sponsored STTP on VLSI design using Cadence tools, analog CMOS VLSI design. The theme of this STTP is analog CMOS VLSI design. Even though the current trends are getting inclined to topics like ML, AI, blockchain technologies, IoT, etc. But the role of VLSI and the subdomain cannot be replaced. Also, expertise in this niche domain, like analog VLSI design, is very rare. Considering this scenario, such rare expertise are available on board for this event. Thus, this event has its own significance, and we are fortunate to be a part of it. Now, I would like to welcome Dr. Deepak Karia, Head of Electronics Engineering Department, to say a few words on this SUTP. Welcome, sir.
Thank you, Priya ma'am. Thank you so much. Let us grace this. Welcome prayers to Lord Ganesha and Devi Bhagavati. Vakratura Mahakaya Suryakoti Samaprabha. Nirvignam Kurume Deva Sarvakare Sarvada. Ya Devi Sarva Bhuteshu Vidya Rupena Sanstha. Namastasya, 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 Namo Nama. On behalf of Electronics, to extend a very warm welcome to our respected principal, Dr. B.N. Chaudhary, Mr. Anil Satoskar from Texas, Dr. Mohammad Hassan from AMU University, the speakers for the day, my fellow colleagues, the Program Evaluation Committee members, Dr. Sukanya, Dr. Reena, and most important, the participants, specifically coming from various colleges and institutions across India. I extend a very warm welcome to all of you. It gives me really, I'm very happy to see most of the participants have been participating in the events from last couple of weeks, consecutive weeks. This is the third FDP of the scenario of electronics department. 3 down, 3 more to go. I really congratulate the team and the members of the committee who have been really being effortive enough to put efforts and showcase their willingness to participate in. Most important, I wish to thank the speakers who have taken their precious time and given some part of their scenarios. I hope that this 1 week deliberation shall be a good scope of learning for you. I wish the participant all the very best and a very joyful experience. Thank you. Over to you, Priya ma'am.
Thank you, sir, for the graceful prayer, and thank you for giving the best wishes for the fulfillment of this SUTP. May I request our coordinator, Dr. Surendra Singh Rathod, to introduce to our program. Over to you, sir.
Yeah, thank you, madam. Good morning to one and all. Good morning to our principal, sir. Good morning. Good morning, all attendees, teachers, not staff. I introduce this second STTP. All of you know that we have planned 3 STTPs. Digital design was already over, and now there's an analog CMOS design. So the people many a times ask, now living in a digital world, everything is digital. There is not necessity of having analog, and therefore why this kind of FDPs on analog CMOS, etc. So one simple answer, which is very illustrative. I can say that, okay, everything is digital. Let us talk in digital terms, and I'll pronounce now 01100110010. So what have you understood? Nothing. So in real life, we are the human creatures, and our real life is analog, and therefore we cannot escape analog. Life will be very boring if it is only in terms of zeros and ones. It is colorful life, and therefore we cannot escape analog design. And to go ahead with this, we have planned many important sessions, and I'm thankful to all our speakers who have agreed for that. So today we will have the keynote speech shortly, and another keynote speech by Dr. Mohammad Hassan. And let me tell you, the planning of this workshop is we start to learn fundamentals. I want to make it clear to the attendees that it is a fundamental training program. It means obviously since first at other places, renowned places, you can discuss research and ask concepts also. But my fundamental belief in introducing this particular course is basic training on the basic concepts of analog CMOS design. Okay, so with respect to that, we have also a team from the Cadence on 3rd and the 4th. They'll be taking you throughout the analog MOSFET fundamentals again, including the layout techniques. Then we have Dr. Pramod Murli from IIT Bombay, who will be talking on analog circuit design for sensor interface. And our very own Dr. Reena Solkusre and Dr. Professor Narendra Bhagat, they will be talking about their case studies. And we have a Dr. S.S. Mark, Institute of Technology, who will take you through the nanoscale op-amp design. And finally, we also have the Dr. Narshad Alam, which you have already experienced. Really appreciated him very much in the first STTP program. We are fortunate to have him again back, taking your few laboratory sessions. And we will end this program with a very, very important validatory session, which will be by Pramod Rao, who is a promoter and electronic systems, who has brought first pager, first Xerox machine kind of things in India. So we have lined up very, very interesting sessions for you. I welcome all of you, and I hope you enjoy all the sessions. If you have any queries, any point of time, we are with you. So over to you, ma'am. Thank you very much. Priya, ma'am.
सर मैम के वेबिक्स का कुछ इश्यू हो गया, यू कैन कंटिन्यू.
Okay, I'll continue, no problem. Madam, can we have next slide in that case?
Yes, sir.
Okay, I'll continue, no problem. So these are the challenges of our design. Okay, so I welcome our principal, sir, for his guidance. He is always with us, we know, and that's why we are able to conduct so many programs. Sir, your kind words, please, address to our attendees and to us.
Yeah, good morning, Professor Rathod and Team Electronics. I mean, I have no words in appreciating the great teamwork you are demonstrating. In a row now, this is the third week, third program, and 3 more to come. Deepak, you are a lucky captain. Yes, Dhoni. You say in cricket, Dhoni is a lucky captain, right? Because he had like batsmen like Kohli and Rahul Sharma, right? So your Rahul is Surendra, who has planned 6 6s, right, in a row, right? And as a captain, you must be happy that you have such players, right? Such professors. Well, friends, let me pick up a thread which Professor Surendra has rightly put. Friends, the word consists of signals and systems, and the word is the physical word is analog in nature. And though Priya Madam said present era is of digital, people talk about AI, machine learning, blockchain and whatnot. These technologies come after capturing the analog word, right? So you capture the analog word, analog signals, then you process it, compute it, and again you have to finally convert your results and all again into analog to deal with the physical words. So whatever is the status of digital VLSI, I'm sure analog VLSI, I mean, that won't affect analog VLSI. Analog VLSI will be important because it sits on these interfaces of physical world and computation, right? And hence, it is very important. It is very niche area, more challenging area, because we know challenges associated with the analog circuits, right? And that's why it is always more courageous and challenging to be an analog designer than a digital designer, right? Where any domain engineer can step into digital competition. I mean, one cannot think of becoming easily without a background. One cannot step into the domain of analog VLSI. It needs background. While more experience you are in digital, normally your old experience is of no use. More recent knowledge you have, more younger you are, it is better, it is said in digital, right? But in analog, it is other way around. More you experience you gain, more mature you become, more skilled you become, right? And that is the importance of analog VLSI, and that is the, I mean, it is very difficult to gain the expertise in analog VLSI, right? Though today, if you look at the size of businesses, analog VLSI may have a very small portion compared to the digital. It is the important, as I told you, because it sits on the interfaces of digital world with the real life physical world, which is analog. I congratulate Professor Rathod for rightly selecting this. From dear participants and faculty colleagues from various institutions, thanks to the AICT for sponsoring our courses, FDP courses. Professor Rathod had two choices. One, to plan a FDP in VLSI and repeat the same FDP 3 times, which was a rather easy route, and mostly people do the same in the country. If you look at on present online version of FDPs, AICT also says ki you may repeat that course 3 times because as it is in online mode. So what people do, they plan 1 week FDP and repeat it 3 times, right? But and there is another, I mean, the other option is you plan independently 3 courses. It is a tough option. Because a lot of involvement, a great work is required, because you need to connect to so many speakers, connect to the arrange for everything, and connect have different participation for these 3 independent FDPs. But looking at importance of a topic, Professor Rathod has rightly selected three topics. One is digital VLSI, one is analog VLSI, and another is a mixed signal VLSI, because we know in real life product, I mean ICs, many real life products are centered around ASIC, application specific ICs, which are, I mean, which is a mixed signal IC quite often. And that's why I wonder, and only Professor brave people like Professor Rathod can only do this in a very short time. I appreciate his efforts. I appreciate the support extended by his team. This program evaluation committee, Dr. Reena, Dr. Deepak, and all faculty members of electronics, you are doing a splendid job. For dear participants, I'm sure this week will be very interesting and learning week, learning opportunity for you. Though the fundamentals, though the course mainly focuses on fundamentals, you will have some different perspective to the fundamental, because many industry speakers, many professional speakers are will take few important, they are the part of this course, they will take important session. Thank you, Aniruddha, for accepting our invitation and being with us at the so odd time. We know it is quite odd to you, but we appreciate your affection to your institution, and I'm sure it might be midnight to you at that. And still you are, and you're with a smiling face, you are with us. Thank you so much. We also appreciate, I am thankful, Professor Mohammed sir from AMU, for accepting our invitation and being with us at this morning. We know the increased burden due to this online mode of teaching learning process, teaching learning, which COVID has forced all of us to adopt, and it has normally increased the burden over faculty. Professor, you must be having your courses and academic load, but still you have found the time and you are with us on this Monday morning. Thank you so much. I am on the behalf of Institute. I am grateful to you. Participants, do enjoy, and I also really appreciate, because terms are on and still you are finding that eager to learn something. It is really appreciating. Friends, this century, this century is very disruptive. It's going to be very disruptive. We have witnessed this technological disruption in last 10, 15 years. Corona itself is a big disruption. We shall land onto the new normal, not only in education, in many walks of life, right? And they say in management, the word has become a hookah word. It is day by day becoming more complex, more volatile, and only mantra to survive in this competition, in this changing world, is learning to learn, and learning, unlearn and relearn, and keep on the journey of lifelong learning. And your participation, your willingness to participate this FDP is a demonstration of that. I really appreciate this act of yours, or this gesture. Though you are on one side teaching, some of you may have classes scheduled, some of you may have laboratory schedule, but you have and you are stretching yourself, and also simultaneously attempting to learn something. I really appreciate. Probably only this attitude will keep the education moving, keep education, in days to come. Thank you all. Thank you, Rathod, for giving me this opportunity to share my views. And I wish you all a big success. Thank you so much.
You truly said, sir, that it's difficult to gain the expertise on analog VLSI design. Thank you, sir, for your kind words and sharing rich experience with us. You've always been a source of inspiration and backbone of our institute. Thank you. As per AICT guidelines, we have formed an evaluation committee. The committee members are Dr. B.N. Chaudhary, Principal of our institute, as chairperson, Dr. Deepak Karia, Head of Engineering Department, Dr. Reena Sonkusre, Head of Electronics and Telecommunication Department, Sukanya, Associate Professor at Electronics and Telecommunication Department as a subject expert. I welcome all members of Program Evaluation Committee. Welcome, sir, and welcome, ma'am. Now I request our coordinator, Dr. Surendra Singh Rathod, to welcome and introduce both of our keynote speakers and chief guests for the day. Sir.
Yes, I am there. Just a minute. Yeah, good morning, everyone. Once again, it is my pleasure to welcome our both the speakers. So first, I would like to talk about the Dr. Mohammad Hassan. I am fortunate that he's with us now, and he's a professor at Aligarh Muslim University. He has been working as a full-time professor since March 2005. He served as a chairman, head of the department from 12th October 2015 to 11th October 2015. He completed his PhD from the University of Edinburgh, UK, on a Commonwealth scholarship in the area of low-power architectures for signal processing and communications. He also worked as a visiting researcher on his own at Royal Academy of Engineering, UK, funded project on the low-power FPGA in the same university. He has published 161 papers in refereed journals and conferences with 1401 citations. He's having many IEEE transaction papers, more than 15 transaction papers, and 47 scope percentage journals. He received Paper of the Year award by the editors of the famous International ETRI journal for his paper entitled High Performance Low Power FET Cores, along with a Best International Conference Paper award. He has supervised 8 PhDs and currently supervising 4 more, along with many MTech dissertations. He has delivered several keynote addresses and invited talks in conferences and workshops. He has filed 3 patents on the design of magnetic RAM, MRAM, and 1 patent on robust SRAM. His research interests are in VLSI design, nanoelectronics, ultra-low power design, electronics, batteryless electronics, variability aware design. He is a senior member of IEEE. Sir, I wholeheartedly welcome you at our institutions, and I'm looking forward after a short while learning from you, because you'll be taking almost 3 hours session for us. Thank you very much, sir, for accepting our invitation. Now, our next guest of honor is our very own student, and we are proud to invite him. I believe that we should always have our students as one of the guests of honor. And Mr. Aniruddha Satoskar is a design engineer at Cirrus Logic, Texas, USA. He is skilled and experienced IC design engineer, seasoned in digital ASIC design and signal processing hardware development. He is a proven innovator with 30 plus US patents issued. His skills include system modeling, MATLAB, Simulink, System Verilog, front-end RTL architecture and design, IP integration, design quality, Lint, CDC, etc., physical design, synthesis, timing analysis. He currently he is design lead on multiple mixed signal integrated circuit projects. He has successfully led of 10 plus engineers on development of high volume ASICs, such as the company's flagship general market boosted amplifier product. He is an inventor on 30 plus approved United States patents on topics such as data converters, dynamic range enhancement, impedance detection, and class edge amplifiers. Experience working closely with the verification, firmware, validation, FPGA prototyping, and post-silicon and product test teams to resolve the hardware issues. He's having an experience of supporting physical design team through backend flows, that is synthesis, floor planning, CTS routing, STS, scan chain, etc. He's having an extensive experience on working with in-house and customer marketing, project management, and systems team for the product definition and product status tracking. He's proficient in architecturing and implementing fixed point DSP filters algorithms and in the digital design and verification of mixed signal intellectual properties such as ADCs, DACs, PLLs, boost converters, etc. He's highly skilled in IP integration with in-depth understanding of various data and control protocols, inter and intra-chip, I2C, S.P.I, all kinds of protocols. He has architected and designed digital portion of flagship ADC IP and worked on diverse signal processing IPs such as decimation and interpolation filters, parametric equalizers, crossfaders, sample rate converters, and delta sigma modulators. Also experiencing DSP core integration and adapters. I cannot simply go on talking his profile. I think Aniruddha is our alumni, and we are really fortunate to have you here, Aniruddha. Welcome to S.P.I.T. and looking forward for your address. Thank you very much. Welcome, sir. And platform is yours for next 15-20 minutes.
Right. Yeah. Thank you, sir. Thanks for the if you can share the slides that I'd sent, that would be really nice. Yeah.
Yeah. Sneha, madam?
Yes, sir. Hello, sir.
Yes, ma'am.
Yeah.
Shall I?
No, sir, I can start. Just a second. Yeah. Is it visible, sir?
Yeah.
Yeah, we can see. So to start off, I want to first thank the organizers of this event to invite me and to give me an opportunity to share an industry perspective on analog CMOS and analog design. As Rathod sir and various other speakers said, it's a niche space, but it is a very important space just simply because the physical world, as we know, is purely analog. So I have some experience with analog to digital converters, digital to analog converters, which essentially captures the boundary between the analog, between the physical world and our digital world where we do all our processing and so on. So if we can move on to the next slide, please. Okay, so the agenda for my talk today is basically these 3 points. So it's always good to start with some good news. So I'll start off with that. Then we'll be discussing some industry challenges that we are facing right now. And then I'll move on to the focus areas for analog design over the past few years and also over the coming few years. So since we are have a time of about 15 minutes, I'll try to keep it more broad rather than going in depth on certain topics. But certainly, if there are any questions, feel free to contact me about any in-depth topics for which we'll be talking about. So yeah, let's move on to the next slide. Okay, so the good news is that semiconductor market has been, the growth in the semiconductor market has been outperforming the world GDP growth for many years now, and that is expected to continue over the coming years. And this is primarily driven by these 3 markets. One is the cloud compute market, which all our high-end performance is driven in these servers that we have at the back end. So all kind of AI, you have the 5G rollout, online work, all that is adding a lot of traffic to these servers. And we have a lot of data processing that goes on there. And in this market, the priority is performance. So you want to be fast, you want to have low latency servers. But nowadays, it's even power consumption is becoming more important in this market because when you have these servers, you need a lot of cooling mechanisms, because now when the servers grow big, you have a lot of heating issues. So power consumption is also becoming important in that market. And then we have the mobile SoC market, which it keeps growing, and it's driven by these smartphone upgrade cycles and wearable growth and so on. So here power consumption is critical because these are battery operated devices. So we are very focused on low power design for these markets. And the third thing is edge computing. Now, this is a slightly newer market as compared to the previous two, and that is driven mostly by privacy issues, where, for example, if you want to do Face ID or Touch ID or Hey Siri kind of applications, what happens is that you don't want to send that private information of the user to the servers because it can be intercepted by some malicious actors. So there is a requirement to do these kind of, even for example, machine learning inference things in the device itself, like in your phone. So that's where this edge computing thing happens, where you do a certain amount of processing at the edge, and then you send some of the metadata over to the cloud, where for if we move on to the next slide. Okay, so that was the good news that the semiconductor market is still growing, but we are certainly facing a lot of challenges as well. So no talk about industry trends is complete without talking about Moore's law, and that Moore's law has really driven the semiconductor industry growth over the past many years. It has led to 1 million times performance increase for processors. But over the past few years, that trend has been slowing down, and certainly it has become more and more difficult for processor performance or memory density to keep up with that trend. So this trend was mostly driven by fabrication, technology development, and architectural improvements, but it was primarily driven by the technology node improvements at the back end. But with more advanced nodes, the fabrication technology development has slowed down, and that, while it has presented a challenge to the industry, it has also put more onus on front-end design. So there's definitely more importance to finding out new architectures to kind of help us keep up with Moore's law. One note I wanted to point out here is that while fabrication technology is at 5 or 7 nanometers right now, like if you see the latest processors by Apple, they actually work at the 7 nanometer node. But when we have these kind of mixed signal ICs, where you have amplifiers, ADCs, DACs, a lot of these ICs are still working at the 22 or 55 nanometer node. And that is because when you have technology node scaling, you get a lot of benefit on the digital side, where your power and area is reduced significantly. But on the analog side, you don't get the same amount of benefit from the technology node scaling, and there is certain amount of additional challenges that you encounter. So for mixed signal ICs, we're still at around 22 or 55 nanometer node. So we can move on to the next slide, please. So one other challenge that the industry faces is called the design productivity gap. And that is, if you see this graph here, you can see that Moore's law has a certain slope over the years. And then there is the hardware design productivity graph, which has a different slope and which is not as steep as Moore's law. And what that really maps is a rough approximation of the number of transistors that, say, a staff design engineer can handle on a particular chip. So that is much lesser than the slope of Moore's law. So what that has led to is basically what we call the design productivity gap, where now you need more number of engineers to develop an ASIC. It becomes very hard to kind of coordinate and make sure that the ASIC that you get is a bug-free ASIC. So there is a lot of emphasis on trying to help fill in this design productivity gap. Now, two things that have helped fill in this gap is one is IP reuse. So you don't have to design the same IPs over and over again. And hopefully you can, with minimal tweaking, reuse IPs. And of course, EDA tool improvements. So Cadence, Synopsys, they played a big part in helping fill this design productivity gap. But still, what we have seen is that the design complexity is still outpacing the EDA tool development. So this gap is still growing, as you can see here. And what is adding to that problem is the fact that now most of our ASICs, they also have a software component to them. So now there is software and hardware interfaces that you need to handle, and that just causes more challenges. So we can move on to the next slide. So those were kind of the challenges that the industry is facing at a very broad level. And now we'll dive into some of the analog focus areas. These are mostly related to analog design and mixed signal interfaces. So the first thing is, CAD tool improvements. Certainly, there is a big need and a big drive for faster mixed signal simulations, because at the lower technology nodes, you have more variation, and to get the same kind of performance simulation. So there is a need to develop faster tools, and there's been the big companies like Cadence in the space who are really working on trying to support that. And then there is also an interest in trying to get this real number modeling for analog circuits. So by that, what I mean is you, instead of running analog SPICE simulations, there is an emphasis not to completely replace them, but to kind of to add on to them real number modeling in system Verilog, where you can actually model resistors, capacitors, inductors, and then move on to more complex circuits like boost converters, buck converters, and so on, so that you can simulate them together in the digital world without running complex mixed signal simulations. So that's about CAD tool improvements. And then there's also talk about the multi-die system in package solutions. And this falls into the same category which I was mentioning earlier, where you don't get the same benefit in technology node scaling on the analog side. So instead of redesigning the analog every time, because since analog variation and characterization has to be done for every node, pretty much the analog IP, even if there's no change in specs, you have to kind of there's a lot of redesign involved in that. So to save around that, there is talk about basically keeping the analog technology at the same node and scaling to digital and having a multi-die system package solution. So there is certainly some interest on the industry side, and there have been some companies who are moving in that direction. But it's still a mixed response, and we'll see how that trend falls out. So the third thing I wanted to talk about is leakage power. This has become a real issue in the lower technology nodes. Certainly, there is a lot of research in the industry side as well as in the academic side about leakage power. And there is work regarding multi-threshold CMOS and power switches and so on to support, to help fix the leakage power issues. And multi-threshold CMOS is essentially where you are able to control the threshold of the CMOS transistor either in runtime, or you can use different threshold CMOS devices based on your application. So you can have low LVT devices where you need faster performance, and you can use HVT devices where you are okay with slower performance, and HVT devices can actually help you save on leakage. So there is a trade-off there, and it's becoming important to partition your design to have these HVT and LVT cells used appropriately. So the fourth point is about solving the challenges associated with high-speed circuits. I won't go into a lot of detail on this, but there's certainly ISI, crosstalk, and other issues that are really challenging with high-speed circuits. And there is a lot of research and work that goes into trying to help fix these issues. So we can move on to the next slide. All right, so this slide, it starts off with the short channel effects. Now these, I think, becomes more prominent in the lower technology nodes. So for those of you who are familiar with DIPL, it's the drain-induced barrier lowering. And what that really manifests itself is that when you have the drain voltage, in lower technology nodes, since you have some drop across the channel, the threshold voltage is not consistent across the channel. So you can actually have your gate losing control of your turning on and off of the device. So that effect becomes more prominent at these lower nodes. And then there are other effects such as punch through, where the drain voltage, if increased beyond a certain point, can actually turn on the channel, even in the absence of a threshold voltage being present on the gate. So there's a lot of these short channel effects, and that used to be kind of on the fringe but now in lower technology nodes, they're certainly very prominent. So the next one is these modeling challenges that we face. So that earlier we used to use these drift diffusion models. These are the standard models for characterizing analog circuits, but they have become obsolete on these lower technology nodes. So there is talk about using quantum models and certain other models which help model the variation at the lower nodes more accurately. And lower nodes is, when I say lower nodes, it's mostly 22 nanometers and lower than that. So there's certainly work going on there. And as I mentioned earlier, since fabrication is becoming, that growth in fabrication technology is slowed down, there is more emphasis on innovative architectures. So for example, one of the things that we have been working on at Cirrus and that we have patented is a multi-path ADC system. So instead of trying to have one ADC where you are optimizing for both performance and power, we kind of split the ADCs into two, where you can individually optimize one for performance and one for full scale, which in turn is relates to power. So you can individually optimize them and then switch between them based on signal level in the digital world, such that it's transparent to the end user. So for the end user, when you're talking into a microphone, you don't see any difference. You think it's a single ADC device. But we are smartly handling that in the digital world. So the last one I want to talk about is the beyond silicon. There is research going on about using 3-5 devices and carbon nanotubes and so on. But this particular topic, there's still research is been going on more in the academic world, and industry has been minimally involved. We may see that change over the next few years, so we'll have to see how that goes. But certainly, I think since academic researchers are still working on that, typically there is a 5 to 7 year flag at least before industry really gets to it. So we'll see how that progresses. I think I got some echo problem, but okay. So I think that was the last slide I had. Yeah. So to conclude it all, I would say that certainly it's a niche area, but there are a lot of challenges still left to solve in the analog domain, and it's a domain that is it's a design domain that's never going to go anywhere, because the physical world is inherently analog, and there will always be a requirement for analog design, and there will always be challenges to solve on the analog side. And typically these challenges are very involved, and you need a lot of background to solve them, and they are certainly more challenging than some of the work that's done on the digital side. So yeah. And in the end, I would say again, thanks for inviting me to give this talk, and it was my pleasure to be here today. Thank you.
Thank you, sir, for sharing your versatile thought. You rightly pointed the challenges of analog design, like power consumption, performance, and privacy, and explained analog focus area in a very nice way. Thank you very much, sir, for accepting our request and taking time from a busy schedule, letting us on industry perspective of analog design. Kindly accept a virtual memento as a token of thanks from our side.
Thank you.
Let us be grateful to the people who make us happy. They are the charming gardeners who make our soul blossom. A statement by Marcel Proust. We take this opportunity to put all good in the form of the words. On behalf of the organizing committee, I would like to thank our respected principal, Dr. B.N. Chaudhary, who graced us with his presence. Your guidance and inspiration always encourage us to carry out a wonderful program like this. Thank you. I extend my sincere thanks to all the program evaluation committee members, Dr. B.N., Dr. Deepak Karia, Dr. Reena Sonkusre, Dr. Sukanya Kulkarni, for the cooperation, support, and input during planning phase of the program. I also extend my sincere thanks to the faculty coordinator of the program, members of S.P.I.T, non-teaching staff for enormous cooperation in the organization of this program. Last and not the least, I want to thank to all the participants for showing the interest for this program. I hope that we all will make this program successful. Once again, I thank you for being here for this inaugural session. All the best to everyone. We now end our inauguration session. Ahead to next session, I would like to request Dr. Mohammad Hassan, Professor, AMU, to deliver his keynote speech for the day.
Morning.
Good morning. Am I audible? To share my
Yeah,
slides
yeah.
first.
Yes, sir. Yes, sir.
Yeah. Okay.
Yes, sir.
Yes, sir. You are audible. Your slides are also visible.
All right. So let me put them in the slideshow mode. Maybe so that. Okay. Many thanks good morning, and many thanks for inviting me to talk about the analog CMOS design. What I really want to do is I have around 3 hours, so I'll just divide this time into different phases, as you will come to know shortly, and then you can interrupt me in between any time if you really want to raise any issue. That's very I keep it very informal so that there won't be really any issue. So you can just pinpoint at the then and there to sort out the problem. So let me have just a warm up first with such a nice first keynote, giving you an idea about the industrial perspective. What I'll try to do, I'll do just the other way around. I'll keep my talk absolutely basic, but before doing that, I'll take you to the some of the current trends as well, just to give you some ideas of what is really happening in the CMOS world. And we are before taking on this topic. So the first, I think I'll highlight the three words: analog, and then CMOS, and then design. So let me start with the analog. I think, and most of the speakers have already talked about why at all we need analog. I partition my talk into the outline will be on. I'll to start why at all we need this analog, why CMOS, and then I'll highlight the introduction. Device, a good time on the device fundamentals, because that's very tricky. And most of the analog circuits, you can just break those circuits into small sub-circuit or key blocks. So I would like to highlight the importance of the key blocks, like the single transfer amplifiers, the cross-code amplifiers, the current sources and mirrors, differential amplifiers. I'll talk about key things about these blocks, so that once you can understand those things, then it will be easy to the frequency response aspect of CMOS, and then about the noise fundamentals, if time permits. I'll take and then let's see how things will move. So let's start first with the motivational part. The motivational part, why is analog relevant? And you all know the real word is analog, and all speakers, they highlighted this point. Would be dead. I think maybe in the 90s or maybe late 80s, because everything is digital. But then people realize that we can't, just because the real world is analog, we need something at the interface for signal conditioning, for amplification, for filtering prior to the ADC, and ADC itself is analog. And then you has to be done in analog. And therefore, analog designers, the requirement came back because you all know that it's very tough to do analog compared to digital. Because in digital, you have to optimize a very small list of parameters compared to a long list of parameters in analog. And you can just see the continuous, all the noise problems and all the variations, because you have a continuous signals on top of it. And therefore, it's very hard to do analog design. And if you are a good analog designer, still you have a good job market compared to a digital, because digital is easy. It can be done easily, and it's highly automated. The level of automation in analog is much lower compared to digital. And still the analog has to be done at the transistor level. Most of analog has to be done at the transistor level. So it's primarily transistor level design, rather than, let's say, in digital, which is like RTL level or maybe system level. So things are much easier in the digital domain compared to what is in the analog domain. So that is the motivational part. Why analog is relevant. Second thing is why CMOS? See, the problem is, if you have an SoC, you have a digital portion and the analog portion sitting on the same chip. So if you use separate chips for digital and analog, then of course you have to do packaging and all things on top of it. Things would become difficult. So why not use the digital technology, which is CMOS, also for analog, and put them on the same chip? And you can yourself gauge the amount of problem that will come. The technology is driven by digital. You have to use the same technology for analog. And that is a nightmarish scenario. And the digital and analog, they are sitting very close to each other. So all the clock lines, noise, and all those bad things in the digital world will come to the analog. So you have to have a very good degree of isolation between the analog block and the digital block if you really want to do the SOC, which has both digital and analogs. And the first speaker highlighted that point. At the nanoscale, real nanoscale, people, they're finding it so difficult to have digital technology and analog on the same chip, just because at the nanoscale, when the channel length is very small, it's very hard to do digital analog, because all the analog properties, they get degraded once you reduce the channel length and to such a small level. And therefore, people are talking about a multi-die solution where you put analog, they are implemented in older technologies compared to most advanced technology for the digital. And therefore, you have a multi-die solution where the analog circuits are realized in older technologies and digital circuits in more advanced technology, just to overcome this huge problem when you want to put both digital and analog on the same chip using the same technology. So, and that's a real thing. That's a hard thing to do at the moment. So let's move ahead and let us see what is. So I think the analog part is clear. The CMOS motivation part is clear. So the CMOS today is the technology not only for digital but also for analog. And what I'll do from now onwards, I'll introduce the third term, that is design, and how the design is different from analysis. So two things are very important here. You have a design part, and then you have analysis part. Now, how the design is different from analysis, and that will be highlighted. So for the design to start with, what you have is you must have a specification. So every design must start with a specification, be it digital design, be it analog design, or be it any design. So, and I think before that, I'll highlight the three courses we have. There's a course on digital system design, that's Verilog or VHDL, where you're designing a system, let's say having 1 billion, it's all digital. Then you have a digital circuit design. Whenever the circuit comes, means you are defining the problem as an interconnection of transistor. So analog CMOS design is also done at the transistor level. So it's say analog circuit design. And the reason why it is called circuit design as an interconnection of transistors. And remember, I'm again emphasizing also the digital circuit is also defined as an interconnection of circuit and analog circuit. They look quite similar. They are primarily done using the same set of tools. So remember that the difference between analog again and the problem is an interconnection of transistors and not as something more complex than that. So let's come to the actual agenda. Specification terms for analog, it's maybe a long list. You have to have a good gain, then the bandwidth, then of course the voltage swings, the input-output impedance. And that's also important. And this list goes on and on. I've just given you some of the important parameters for the analog design. What else you have is you must decide the technology in which you want to implement your design. So two things you must have. You must have a specification. As a designer, the information about the technology that you have to choose to implement that design, depending upon the budget that you have or whatever else you want, or depending on the client's insisting on a particular technology. So you must have what's called the specifications along with the technology in which you want to implement these specifications. And of course, what you end up in is you must have what's called the process design kits or the PDKs. So what you have, a list of a specification and the process design kits, which is application house or the technology in which you want to implement your design. And this process design kits will have information about if I implement it, let's say in CMOS, MOS models I have, I must know the different parameters, advanced parameters of the MOS models for a given technology in which I want to implement the design. Then I should know how to implement the resistance, how to implement the inductance, how to implement the capacitance in that technology. If at all I have these components in my design, then I should be able to realize these components also without any problem. Now, the important thing is that the PDK, you have to get it from the foundry in which you want to implement your design, and you have this specification. Now, let's see how to move forward. PDKs, the process design kits, which contains information about all aspects of design. Let's say the devices that are there, MOSFETs, like resistance, like capacitances, like inductances, plus all the layout information about of these devices, because layout is a very important and integral part of the analog CMOS design. It's an integral part, and therefore the layout information has to be also based on the specifications. Now you have to look for the circuits which are available in the literature. Okay, gain do I need? How much bandwidth requirement is there? What are the voltage swings are there? Technology in the literature will most likely meet this specification they have. They have to need a wheel, they will be able to satisfy the given specification for a given technology. And the most opinion will be able to meet the specifications from the literature. Now, to do is give the given specification. You have to come up with a circuit that the important message is that from day one, whatever designing you are doing is dependent. So whatever designing you do is technology dependent from day one. And that is the most important thing that you have. So you have to do a literature survey, find out, find out the circuit that will most likely match the given specification. For instance, if I want a high gain, I have to choose from the literature what are the high gain amplifiers that are having in the literature, and let's say what are the pros and cons of these amplifiers, whether they are able to have the required swing that I'll be able to. That is the part of the specification. Whether the bandwidths are in the required domain or not. So really, we have to think about from the literature, find out which circuit will be most likely to meet the given specifications that we have. And once we have narrowed on the circuit that we want, that will most likely meet the specifications, then we will adjust the W ratios of the different transistors which are forming approximate models that we have. The most important thing is using the most approximate models under the control of the designer for the different MOSFETs which are part of this circuit, which will You have to set two. The most important thing is, given a specification, you have to set the biasing current first. What power is supplied in current be less than what is there in the power budget as part of the specification. So first of all, you have literature, if you are able to meet the specifications, you have to set the WIL ratios by replacing each transistor by its most approximate model and then finding out the gain, bandwidth, and all the other important parameters. Now, to understand a complex circuit easily, you have to break the complex circuit into small got a current mirror, and then it has got, if you look at this part, if I look at this, this is my current sink. So what I have done is, whatever circuit I'm having, I can always break this circuit into smaller components and then look into the functionality of these components, look into the design aspect of the most approximate model of the transistors which are forming this circuit. Now, if I'm able to meet the specifications with the given W, depending on the area budget that I'm having, then it's fine. If not, then I have to tweak the circuit, which is already available, and go on doing design through hand calculations till these specs are roughly met. Remember, hand calculation of analog design, which is a part of phase one, is a key thing or the most important thing for an analog designer. An analog designer, the most important thing is designing, trying to meet the specification using hand calculations by using the most approximate models of the MOS transistors, because you cannot really use complex models in the which will most likely meet the specifications, and then find out what are the value WIL ratios by using the approximate circuits, MOS models that you have, and then for a given technology, old technology, and then trying to meet the specification values. And go on doing it till the specs are met. If you're not able to meet the specs, then modify the topology that you have till these specs are met. And remember, the biasing current is always set by the power budget, because once the biasing current is set, all the other important parameters of the MOS transistor will be available, and then you can decide the WIL ratios for a given specifications. And this is the most important part, or the most challenging part of the analog designer, doing the hand calculations, so that you should know if anything changes and arrive at the what I call a crude WIL ratios value. Remember, the tools, the EDA tools are there only for helping you out. The most challenging part is the hand calculation part using the approximate models. If you are not able to understand the circuit that you are designing, if you're not able to understand the circuit that you are designing, you are absolutely blind. You are at the mercy of the tools. The tools are there to help you out. Whatever you are doing through hand calculations, you are verifying whether your hand calculations are correct or not. So you just verify whatever design specs you have achieved through hand calculation, whether the same trend you observe through EDA tools. I can understand that. Today the models are very complex. They have third order effects or second order effects also incorporated, which you can't catch in the hand calculation. Even then, the hand calculation is the most important starting point. It will be you will get the guiding values of the WIL ratios from the hand calculations. And once you get the guiding values of the WIL ratios through hand calculations, then only you have to use the tools. So tools are there only for assistance of the analog designer Once you have done the hand calculation, decided on the topology, which will most likely meet the specifications, then only you can think about and adjust the W by L ratios, and then only you have to use the tools, whether the same results are replicated with the tools, whatever you are observing through hand calculations. If the trends are radically different, then you have to answer why. If I'm getting some gain X through my hand calculation, and if I'm getting some very radically different values of gain through simulation, then I have to figure out what is causing that difference. So understanding of the circuit is of paramount importance for an analog designer, and the only way you can do it is through hand calculations, finding out how things are moving. Unless you have complete command over that, you can never be a successful analog designer, in my opinion. So the most tough part is understanding the circuit and trying to handle the different values of the parameters which are part of the specification and try to meet the specifications. If you can't do it, then you part of the analog designer. First part is arriving at a circuit, setting summarize all these things with some of the slides. Okay, so the understanding the computation of a specification using approximate device model is the key attribute of an analog designer. So that is the most important aspect. And of course, then you can use all the tools from Cadence like Spectre for circuit simulation or Virtuoso for entering the design at a later stage. Once you have already come up with the rough value of the W by L ratios through hand calculations, that is the key thing. So don't be at the mercy of the tool. Learn the art of hand calculations. That is the message today. Without hand calculations, if you are not able to predict the given specification, you're absolutely blind and to the mercy of the tool. Never be blind. Understand the circuits. Only then you can achieve the goal in the shortest possible time. So let's move ahead. Now, this is what I have put it in this typical design steps. You have to select a previous design that is most likely able to meet the specifications by doing a thorough search, and then find out the attributes, analyze that circuit that you have, and investigate its plus and minus points as per the specifications. You have to modify the existing design and then recompute the specification parameters through approximate device models through hand calculations. And once you have arrived at the biasing currents and the W by L ratios, only then you have to use the simulator tool and investigate if there are differences between the approximate and the exact value of specifications that you're getting through simulation, and justify. If you're not able to justify, there is a serious problem either with your simulation or with your hand calculation. So that's the important message. And therefore, the hand calculation part is the most crucial part for an analog designer. You have to understand the circuit. You will gain this through experience, through innovations. It's really hard, but then that is the real way forward, because analog design, you all know, it's not really an easy way out. Let's move ahead. Now, in order to understand the complex analog circuits, let's say like A to D converters, D to A converters, switch capacitors, or maybe other systems, you have to really partition it into subsystems like current sources, sinks, mirrors, switches, single transistor, differential cascode amplifiers, OTAs, comparators. So that's very, very important, because subcircuits are the building blocks of these complex systems. And of course, at the lowest levels, you have the MOSFET. You have to understand the MOSFET. Without understanding the MOSFET, you really cannot do CMOS analog design, because that is the. So you have to understand the device physics. You have to understand the device physics, which is required to understand the analog CMOS design. You should know how the resistances are work, how the capacitance really works, how the inductance really works, if they are the components in your design. So that these things must be clear. Only then you can create an analog chip. So let's move ahead. Now, this is just what I have already covered, and again, it's the CMOS op-amp, and you can break it up into a differential pairs. You must understand how the differential amplifier really works. how the current mirror works, what are the key attributes, and then how the single transistor amplifier works, and go on. So for any complex analog chips, you can always break it into the key blocks or subcircuits. So my job is, first of all, you have to understand the MOSFET. That's the first key thing. The second key thing, the functionality of the basic blocks, which are the building blocks of big analog circuits or systems. So once you understand this, then other things will be just a smooth walk. So today's job is to convey the basic functionality of a MOS transistor from an analog perspective, and then some of the key attributes which will help you in understanding analog CMOS design. So I'm keeping the lecture very, very simple and very basic, so that you'll be able to have good fundamentals to build this on as this whole course progresses. Many more complex things which will be coming to know, you'll be coming to know later. So let's move ahead. Now, I think I don't know how many of you are familiar with the layout. So I've just given this a layout. This is how the inverter looks like, which can also be inverter is a dual circuit. You can use this as an inverting amplifier also, and you can use it as a CMOS inverter. So it has both digital when it operates in the stable region, and when it's operating in the transition region, you can use it as an amplifier. And this is the corresponding layout. How the layout of this looks like, and then the cross section is available here. So my important message is, this is the view that you know. This is my circuit view that I have showed you, the phase one. And the second phase of this analog design is the layout view. This is the layout view of the same inverter. So the layout is very, very important, because the layout you have to submit to the foundry for fabrication. So then there should not be any disparity between the circuit view and the layout view. The circuit view and the layout view must be identical. Only then I'm sure that my layout, it doesn't have any error. It does conform to the circuit which we have already designed. And therefore, the layouting is a very important phase of the analog IC design process. I'll highlight the flow very shortly, but before that, it's very, very important to tell you, I don't know, I can't really have the time to go into the layout aspect, but how to create the layout. Hopefully, I think some of the person will be talking about the analog layouts, about those things. But the most important thing is, layouting is the one of the most important part of the analog design process. So I've already talked about phase one. The second phase will be the phase two, which is the layouting phase, how to get the layout from a given analog circuit. And once you have done the layout, then you have to go to the third phase, that is your fabrication and testing. So let's move ahead. Now, this is the typical IC design flow. I have highlighted first the phase one, and the background phase of the phase one, I have not really touched upon it. That touched upon in great detail. That's the phase one. Now, in phase one, you already know you have to arrive at a circuit that will meet the given specification. Not only the circuit, through hand calculations, you have to arrive at the W by L ratios and the biasing current of this circuit that will meet the specifications that you have in a given technology in which you want to implement your design. So you have the technology on one hand, you have the specifications on the other hand, and then you have to carry out the design using most approximate model through hand calculation by doing a thorough literature survey, identifying a topology which will most likely meet the specifications, and then work on that topology, adjust its WIL ratios till the specs are met, or maybe tweak the circuit, existing circuits, or maybe modify it radically till the specs are met through hand calculations. And once you have done it, then only you can enter the design through a schematic, virtuoso schematic editor if you're using Cadence. And the phase is called the front end phase, or the front end design. That is, you enter the design, and then you can use either SPICE or Spectre to carry out the simulation. So once the hand calculation is over, you can do the simulation by entering the circuit using the PDK of the technology in which you want to implement your design. So once you have done the schematic design, you can do SPICE or Spectre simulation. and then till all these specs are met. So after this, I think it's an iterative process. Go on modifying the schematic, you go on adjusting WIL, fine tuning it till these specs are met. And but the starting point for this whole thing, the starting WIL ratios will be the one obtained through hand calculation. And of course, you have to tweak them in a logical way, because through hand calculation, you've already understood the functionality of the circuit and how things will really move if you increase or decrease the WIL ratios of the different transistors, and then find out and do a lot of iterations till the specs are met using these exact parameters which you will get through the PDKs of the technology in which you want to implement your design. So once the specs are met through circuit simulation, it means that your schematic entry and simulation phase is over, or your front end phase is over. Or I would say that the phase one is over. Phase one is adjusting the WIL ratios through hand calculations, adjusting the biasing currents depending on the power budget, and then identifying the topology in which you want to implement your design. And then after that, you use the cadence tool for verification using the exact models which are part of the PDK of the technology in which you want to implement your design. Do it in an iterative way till all these specs are met. So your front end phase is over. This is the most challenging and the most important phase of analog design. Now, once this phase is over, you move to what's called the back end. The BE stands for the back end phase. Now, what is this back end phase? Back end phase is whatever your circuit view, you have to convert this circuit view into a physical view. So this is a circuit which I have designed. This is my circuit view. Now I have to do its layouting. So what I will end up in is my layout view or the physical view of the given circuit that I'm having. Now, this given circuit is basically in terms of the interconnection of transistor circuit view. Then this is the layout view, how this circuit will look like on the chip. When I look at from the top, it contains information about the different layers. And I can just talk about layout. Today layout, number of transistors, let's say on digital is more than 10 billion. And then you have 10 metal layers or of interconnections of copper. It's really a complex thing. So, but for analog, it's the number of transistor count is always limited. It's not much, and therefore, this is a very simplistic layout of, let's say, this circuit, and this you have to do through the actual physical placement of the transistor using the virtuoso layout suite from Cadence. You have to do the placement of the transistors. Then you have to carry out the routing, and once you have placed the transistor, you have to carry out the routing between the transistors on the and then you have to use what's called the DRC, the design rule checks. And the DRC rules will be available in the form of the PDK. And once you have loaded the PDK, automatically that PDK will be invoked. And then the layout will be checked for any design rule violations. If there are any violations, it will be flagged. And accordingly, you can modify the layout till all it's free of any design rule violations. And once you have done it, you have to go for what's called the layout versus schematic. What it means that it converts the layout back into schematic. Now, traditional, the back end, it converts the schematic into layout, but this LVS do the reverse. It converts the layout back into schematic to really find out whether this layout does conform to the schematic. It's double check because fabrication is expensive. We have to be absolutely sure we should get first time silicon success. So we'll do everything to ensure that our analog design will be devoid of any error, especially our layout should be devoid of any error to ensure that that LVS is done to ensure that whatever layout we have done, it does correspond to the schematic from where we have started. So once LVS is extraction, and once we have done the parasitic extraction from the layout, because these parasitics will be available only when you have the length of the interconnect and all those things, and then only you do what's called post layout simulation. This is again a very important phase, and this simulation will be with all the parasitics of corresponding to the interconnect included. And once it is done, your spec is finally met. If your spec is finally met after layout, after the backend phase, This is the farthest that you can go in the simulation part. You can't go beyond that. And then whatever layout you have done, you can generate a GDS2 file, which means that once you submit that file to the foundry, it's ready for fabrication. And once you have done the fabrication part, then the last part is the fabrication and testing. So this is the last part, because once after fabrication, you must have a testing strategy, how to test the design, to ensure that even after testing, all these specifications must be met as per your design. And once they are met, your product is ready for market. So that is the basic steps. What I have done is I have divided it into three broad phases. The first phase is the hand part, and I will stress that phase because that is the most important phase and the most challenging phase also for the analog designer, to come up with a circuit that will meet the specifications. Come up with the circuits with the W by L ratios and the biasing current, which will most likely meet the specifications. And once you have the W by L ratios approximate, then you have to use the verification tools like Cadence, like this Spectre, S.P.I.T for circuit simulation. And remember this, the tools are there to help. The tools are not, you should not be at the mercy of the tools. Remember this statement is very, very important. And after that, once your phase one is over, it means whatever circuit you have come up, that circuit is able to meet the specifications in a given technology that you have, the complex model of the technology rather than the approximate models which we have employed using hand calculations. And once we have done it, the second part is what's called the physical view, how to get the layout. And then these are the different steps of the layout. And once the layout, after the layout, what we get? What we get is the parasitics. And then we have to again do the Spectre S.P.I.T simulation with parasitics, because those parasitics we had ignored in the front end phase. So this is the most important phase. Even after the post layout netlist simulation, it's possible that some of the specs are not met. Then we have to go back to the placement of routing, or you have to go back to the schematic and again modify our design till the specs are met. So remember, our specs will deteriorate because once we include the parasitics. So layout is the most important phase of analog IC design after the phase one, because after this, you'll come to know whether you are able to meet the specifications if the parasitics are included. And then once all these specs are met, then the design is ready for fabrication, and you move to phase three, that is fabrication and testing. I hope this slide, because this is very, very important slide. That's why I've put a lot of stress on this analog IC design flow. If you have any questions, you can ask me right now. Otherwise, I'll move ahead. All right. So let's move ahead with what the different analog design challenges. You must be wondering why the analog excites people even today, and why does it excite? Because analogs by the day is becoming more and more challenging. So before taking up the basics, it's better to highlight the problems. Imperfect MOS transistor at the nanoscale. That is the biggest challenge. Today, I would say the MOS transistor has become very unreliable. No two MOS transistors will have the same threshold voltage on a chip. It's because of so many fluctuations. So you get a spread in the threshold voltage. This spread you may tolerate in the digital domain, but it's hard to tolerate in the analog domain, because threshold voltage is the most important parameter, one of the most important parameters in the analog design. Declining supply voltages. You can design good analog circuit at 10 volts, 5 volts, no problem. What about designing the same analog circuits at 1 volt? Many circuits will malfunction, will fail. So you have to hunt for new topologies which will be able to work at lower and lower supply voltage. So you need to do a lot of innovations. There's a possibility of a lot of innovations in the analog world, especially when you are working at supply voltage of 0.5 volt, 0.6 volt, and 0.7 volts, and even lower. So today we are moving into the era of what's called batteryless electronics, like IoT nodes. I want really to charge these nodes, not on batteries. So I want both the digital and the analog part to operate, to consume minimal power. And they should operate at the least possible voltage if I can. Digital voltage has to be reduced. so that the power budget can be of the power budget of the batteryless electronics can be met. It's a huge challenge. How to do analog design at low voltage and still combat noise? It's not easy. It's very, very tricky. There'll be a lot of supply voltage variation, process variation, temperature variations, especially at the nano scale. How to ensure the working of the analog circuit in the presence of these variations? Huge challenge. Another is increasing complexity of analog circuits. You have to handle more and more transistors for analog design, and that makes the circuit more complex and its simulation more difficult. And the worst part is, in some of the SoCs, the digital and analog circuit has to sit on the same chip, and therefore you can see digital, analog, digital. So many signals are varying, and you have all crosstalks. It's a huge, huge problem coming from the clock lines. Noise will come on the supply lines, and that would be a nightmare. You have substrate noise, you have supply voltage noise. It's a huge, huge challenge of designing an SoC with both the digital and the analog portions sitting on the same chip. So these are the challenges, because I think this really enthuses you that there are so with the technology direction in which we are moving, and people are scared of it. That's why they're using an older technology, because realizing analog in today's technology is so hard that we have to restrict analog to, let's say, a 90 nanometer node or 65 nanometer node. We don't want to go below it because the transistor, because the functionality, we are not able to realize the functionality. It's a huge challenge how we can do it, and it's not. There's no easy answers for it. Okay, you know the different parameters for the analog design. This highlighted the octagon. You have noise is a huge issue. Then, of course, power dissipation is always an issue. Then you have the most important parameters like gain, the supply voltage that you have to choose, the voltage swings, and then, of course, the bandwidth, the speed, the input-output impedance, and, of course, the linearity is also important. And there are many more parameters for the different outputs. I have the most important ones. Let's move ahead and try to understand. Now this is the basic introduction part is over. Now, in order to understand the analog CMOS design, what is most important is you should be able to understand the device fundamentals. Without understanding the device, it's extremely hard to understand what this analog design is all about. So what I'll do is I'll go through, because I think this is something very basic, but I'll sail through the MOS so that you can recollect important things which will be useful from the analog perspective of, let's say, a MOS transistors. So let's move and try to understand the device. Now, device can be anything. It can be a FinFET, it can be a MOSFET, it can be a carbon nanotubes FETs, it can be a tunnel FET. The device can be anything. Device is basically the basic building block of the circuit that you want to design. If you want to design in the carbon nanotubes FET op-amp, then you must be conversant with the CN-FET fundamentals. Here, my concentration is on CMOS, and therefore I'm bothered about to explain the fundamentals of a MOS transistor. And how to understand this fundamentals of a MOS transistors, what I must have are the two parameters, the IV characteristics and the CV. Now, this is true for every device. If I have invented a new device, I must be conversant with the current voltage characteristics, the relationship between the current and its voltage, the terminal voltage, and the relationship between the capacitance and its terminal voltage. Because capacitance will give me frequency response characteristics, and the currents will give me the most important resistance of the device and the transconductance. The transconductance and the resistance I can extract from the IV characteristics, and from the CV, I will understand the different capacitance of the device. And this capacitance will be handy for all the frequency response analysis. And this IV will be handy for computation of all the other parameters, because the transconductance and the resistance will be clear from the IV. Now let us try to, because, and once I can do the same thing for CN-FET, for tunnel FETs, for carbon nanotubes, FETs, for single electron transistors, or for any or maybe for this any upcoming device. I should know its IV and CV, and I can capture this, let's say, in a Verilog A model. If I have a Verilog A model of an upcoming device, or a SPICE model, or maybe so I can simulate that device and see how does it really work. So remember, I should have the IV and the CV. Now let us try to start with my own with our own device, that is the MOS transistor, which you really want to understand. And you know all these things, but I'll try to again it's basically a review part, and I'll quickly go through it. You know, this is the cross section of a traditional long channel MOSFET operating in the ohmic region or the triode region or the linear region, where you have the defining moment is a small VDS. This is small VDS. The drain to source voltage is small, so that you have a channel extending from the source and the drain end, and the gate to source voltage must be more than the threshold voltage. Under that situation, what are the important characteristics that I have to highlight for this traditional MOS transistor? Now, before going to that, let us talk a bit more on some of the generic parameters about the MOS transistor so that you can appreciate its functionality in a better way. Now, what is important in this, if you look at this MOS transistor, luckily we don't have any gate current. So the problem is, if I have the IV, my only current I is luckily this drain current. So this is the big advantage. It has made my life simple because the current is only the drain current I am having. Now, the drain current depends on three voltages in this. The first voltage is the gate to source voltage, because the gate to source voltage will increase the channel dimensions, and then therefore the flow of current between drain and source will go up. So the drain current is a function of the gate to source voltage. The drain current is also a function of the drain to source voltage. If the drain to source voltage goes up, then this drain current also goes up, and that's what we have found in case of the MOS. So the drain current is also a function of the drain to source voltage. And what is the third important voltage that we have? Now the bulk is grounded. The bulk is grounded, and the source may be at ground potential. It may not be at ground potential. If it isn't ground potential, fine, then VBS will be 0. If it is not at ground potential, then you get some VBS, non-zero VBS. You'll come to know that the drain current also does depend on, the drain current will be a function of VGS, it will be a function of VDS, and it will be also a function of VSB, the source bulk voltage. So there are three voltages, terminal voltages, on which the drain current of a MOSFET depend. Remember this very easy relationship to understand. So drain current is a function of the gate to source voltage, is a function of drain to source voltage, is also a function of source to bulk voltage. As you will come to know through body effect, the source to bulk voltage will be able to change the threshold voltage of the MOSFET and indirectly affecting the drain current. Now, I'll say that the drain current is a function of VGS, the gate to source voltage. It's a function of VDS, the drain to source voltage. It's also a function of VBS, the bulk to source voltage. Now, the relationship of drain current with VGS. Now, this is a very important point. The ID-VGS relationship. In a good transistor, ID should be a strong function of VGS. A small change in VGS should cause a large change in my drain current, which is flowing between drain and source. This will quantify, this will decide the quality of the transistor. The quality of the transistor depends on, because my input is stationed at the gate. If I want a small input change at the gate, should cause the largest possible change in the drain current. That is the most important. If I really want to get a good gain, a small input change should cause a large current change. And that can only happen, that is basically this property of the MOS transistor is captured between the drain current and the gate to source voltage in this property is called the transconductance. Transconductance is the ratio of, given a small change in VGS, what will be the corresponding change in del ID or the drain current? And I want this value GM to be as large as possible in a good transistor. Remember this very important fact. about the transconductance GM, and that for a good transistor, this should be as high as possible, or a small change in drain current or a small change in gate to source voltage should cause the largest possible change in drain current. And that is a very important design metric or a very important property of the MOS transistor. Now, the second dependence, the ID, the drain current, is also a function of VGS. Now, unfortunately, I don't want the drain current to be a function of drain to source voltage, because I want the gate to source voltage only to control the flow of current between drain and source. But unfortunately, what happens, the drain current does become a function of the drain to source voltage. So that parameter is called the GDS, or its reciprocal is called RDS, the most important resistance of a MOS transistor. So GDS will be del ID. If there occurs a change in del VDS, what will be the corresponding change in ID? And that is reflected in GDS. So ideally, I want a low value of GDS because I want VGS to be the boss. It is the VGS that should cause a maximum change in drain current because the input is fed at the VGS. So a good quality transistor should have the highest value of GM and should have the lowest value of GDS, because I want GDS to be as small as possible to get the largest value of RDS. That's important. I don't want ID to be a strong function of VDS. And similarly, I don't want ID to be a strong function of VSB. And that's the last one, is also a transconductance, because the current and voltage are at different terminals. And since the current and voltage are the same terminal, this GDS is your conductance, and GMB is your transconductance, because it's del ID divided by del VGSB. Now, these are the three parameters on which the drain current depends. And from these three parameters, you can extract the small signal model of the MOSFET. So we have to compute GM, the transconductance, we have to compute GDS, and we have to compute GMB. And all these parameters, small signal parameters, which are small changes, can be computed once we know the relationship, the large signal relationship between ID and the different voltages that I have. So in different regions of operations, we have to find out how the drain current is related with VGS, VDS, and VSB. And based on that, we'll extract the small signal parameters like the transconductance, the GDS, and the GMB. Now, before moving forward, I can even now start with this very important factor. This factor will help you out, because one of the most important properties, the gain in case of analog. And the gain, as you'll be coming to know, is the product, the intrinsic gain or the maximum gain that you can extract from a single transistor is the product of G, because at the output you always get at the drain to source, VDS, and the input you apply at VGS. Now, GM is del ID by del VGS. If I multiply it by RDS, what I'll get is del VDS divided by del VGS, and that I want. And del VDS is the output voltage change, and del VGS is the input voltage change, and the ratio will be the gain, and that ratio will be equal to the product of GM and RDS. So you can write down here this very important point. If you want to get a maximum gain in a MOSFET, you must have the highest value of transconductance GM and the highest value of RDS, the drain to source resistance, so that the product is maximum. And that is the property of the MOS I'm looking at. This is the ideal MOSFET. If you want to compare two MOSFETs or compare two devices, what is its GM and what is its RDS vis-a-vis MOSFET? And then you can very well see whether that device will be better than a MOSFET or inferior to a MOSFET. So this is a very important background stuff before really taking off a MOSFET in linear mode. We can take a break whenever you feel like that, so that because it's already 11:31, you can tell me whenever you want to take the break, and I'll be ready with it. There is no issue. So you can raise that point. I'll stop for 15 minutes. That's not an issue. Whenever you feel like that. So my agenda is I would like to just very quickly finish this basic transistor if I can, within that time before taking a break. But you can decide whenever you feel like doing it. Okay. Now, in this linear mode, the MOSFET, you have a channel between the drain and source. And in this linear mode, I would like to compute the value of transconductance GM, GDS, and maybe GMB to find out whether the transistor will be this MOSFET will be a good transistor if I really want to realize it, use it as an amplifier in the linear mode or the ohmic mode. And let us see how does it figure out, and that will be clear in the next slide. Let's move ahead. All right, so I don't want to go into the derivations. I think you can get it from in the standard text. Now, in a linear mode, the basic thing is you must have a channel between the drain and the source. And for that to happen, now there are two voltages which are responsible for creating the channel. If VDS is equal to 0, there's only one voltage, VGS. So VGS has to be more than VT if we want the channel extending from the source towards up to the drain. Now, if I apply VDS also, then channel is a resistance. So at the drain end, I have this highest voltage corresponding to VDS, and the voltage goes down as I move towards the source. Now, so there's a variable voltage because of the drain as I move from drain to source in the channel. Now, there are two opposing voltages. One voltage is VGS, another voltage is VDS, and that two opposing voltage, the difference of that voltage should be more than the threshold voltage. So if I want to ensure that there will be channel throughout there will be channel existing all the way from the source to the drain. The VGS minus VDS should be more than VT. That is the condition for a channel to exist throughout. And that condition, from that condition, you will get this. VDS should be less than or equal to VGS minus VT if I want to have a channel between the source and between all the way from source to the drain. And if that is the condition, we are operating in linear mode, and the relationship between the drain current and the terminal voltages are this. This is the large signal condition, and you all know this: Kn dash W by L VGS minus VT into VDS minus VDS square. Remember, this VGS minus VT is a very important term which we'll be using again and again, and this we call it an overdrive voltage. Overdrive voltage. This is the difference between VGS minus VT, and which we'll be using quite often. Remember now, the important parameters for the drain current. ID will be Kn dash, which is mu and Cox, is a process transconducting parameter. Remember this, mu n is a carrier mobility. Now, one thing which I really want to highlight, it's very interesting. MOS transistor has not changed for the past 50 years. What we have been doing is we have been making the channel length smaller and smaller, starting from maybe around 25 micron for the first device. Now the channel length has gone down below 10 nanometers. And I think TSMC has already rolled out, I think, 5 nanometers, and they are in the process of rolling out 3 nanometers between source and drain. A few atoms left between source and drain. This is from where? But I think people have realized that the Moore's law will no longer be valid, I think, after 2014. So they've moved on from a traditional CMOS to what's called a 3D CMOS, like a FinFET. But I may be wrong. In my opinion, now, in order to sustain the Moore's law far in the future, we have to really change the device type more quickly than we used to have in the past. So maybe FinFET may go up to 2025, and then after that, we have to look for maybe a carbon nanotubes FET, or maybe I don't know, a gate all around, and or something else will come up in that time. So now there's a big innovation required at the device level if you want to sustain the Moore's law far in the future. Okay, so the important thing which I really want to say is look at this, the drain current, the mobility term is coming. Problem is this MOSFET has got a poor mobility. And carbon nanotubes FET has got a much higher value of mobility mu, and that's why everybody is talking about carbon nanotubes FET, because it has got a very high mobility compared to a MOSFET. So Kn dash for the carbon nanotubes FET is very large, and therefore, for a given gate to source voltage, you'll end up with a much larger drain current compared to MOSFET. And so you get all the good attributes like high transconductance in the carbon nanotubes FET compared to what you get in MOSFET. So the mobility, we have to look for devices, materials in the future, which has much higher carrier mobilities compared to compared to MOSFET, if you really want to replace it. Now, this expression, I can minimize the higher order term. I can assume it to be negligible because for this linear mode, VDS is very small. And if VDS is very, very small, I can use this approximation and then calculate the most important two parameters, RDS and GM for it. And what I've got is this. GM is Kn dash W by L into VDS. 1 upon del I, this is the value of RDS. Now it's very clear. In this region, the MOS transistor behaves like a voltage-controlled resistor. So this is the most important property of a triode or a linear or an ohmic region where the value of VDS is very, very small. It is indeed lower than VGS minus VT. And if I ensure that the VDS value is very small, then the RDS will be nothing but the MOS transistor can be replaced as a voltage controlled resistance. So if you want a resistance in your circuit anywhere, you must ensure that you can use a MOS transistor as a resistance, provided it operates in the ohmic region or it operates in the triode region. So in any analog circuits where it is required that the MOS transistor should be used as a resistance, we can use this linear mode. I'll tell you why we cannot use this linear mode in whenever I want to realize a MOS transistor for amplification purpose, because I'll show that get in the ohmic region or the linear mode is much lower compared to what you get in saturation. And therefore, the MOS transistor, when you want to use it as an amplifier, must be ensured to operate only in saturation and not in the ohmic region, so as to get the required value of transconductance that you need. That's the high value of transconductance. Let's move ahead. Now, this is the most important region, which you'll call it, what's called the saturation region or the strong inversion region. And then the condition is the VDS, the drain to source voltage, should be more than the gate to source voltage, more than the overdrive. And for this, of course, if I have this condition, I won't get the channel at the drain end. There will be pinch off because the voltage difference between VGS minus VT will be less than VT. And if I put that condition, I'll arrive at this VDS minus. So for this to exist, VDS should be more than VGS minus VT for a long channel device. Of course, for a short channel device, things will be slightly different. Now, if I use this VDS should be more than VGS minus VT, I have arrived at this very important expression. And this I can derive from the previous expression by putting VDS equal to VGS minus VT. What I'll do is, in the previous expression that you all know, this previous expression of current, what I'll do in this expression, if I replace VDS is equal to VGS minus VT, that's the value corresponding to the edge of saturation, then I can compute ID, and the value doesn't change much. So I'll get this expression. This is the value of current, drain current, dependence on the different important terminal voltages. Because with this, I can extract all the small signal values. This is the large signal relationship of drain current with the different important parameters, which is your VGS minus VT and 1 plus lambda VDS. Now, one important comment about this expression. Now, this is the most important factor. You all know this overdrive voltage. Now, in this region, what you'll find that the drain current is a quadratic function of the overdrive voltage. So drain current as such is a quadratic function of the overdrive voltage. And look, the relationship between GM and it is del ID by del VGS. And then the drain current is also dependent on VDS through this 1 plus lambda VDS term, where lambda is your channel length modulation parameter. And this basically highlights how the drain current depends on the drain to source voltage. And this lambda has to be introduced just to highlight that dependence. If lambda is equal to 0, there will be no dependence on ID on VDS. In reality, ID does depend on VDS, and that will be captured by this expression. But the important point is lambda is proportional to it is inversely proportional to the channel length. It can be proven, and therefore, if I want this dependence to be feeble, I want to have low value of lambda. And low value of lambda I can achieve only at much, much, much longer length of the channel. So if I have a longer channel length, I have a small value of lambda. In a good transistor, I want lambda to be as small as possible because lambda decides what will be RDS, the drain to source resistance, because this del ID by del VDS is your GDS, if you recall from the previous slides. And therefore, I want ID to be least dependent on VDS, ideally zero. Lambda should be zero. But if I want to have lower lambda, and lower lambda I can achieve by using longer channel length devices. That is the problem at the nanoscale. At the nanoscale, the channel length is lower. So if the channel length is lower, my lambda is very large. And if my lambda is very large, my GDS is also large, and therefore the RD is small. And therefore, all the amplifier, if I design at the nanoscale, they'll be having very poor gain because the value of the drain resistance is very, very small. And that is the problem at the nanoscale. I cannot use minimum channel length devices for the simple reason that the lambda, if I use minimum channel length devices, the lambda will be large. That is the biggest problem at the nanoscale. And therefore, if I want high gain, I have to choose longer channel length. That is the most important problem. And that will be clear from the next slide. Now this is the output characteristics of a long channel MOSFET. I think everybody knows about it. And look at this. This is the, okay. This is the quadratic dependent. This is important. ID is a quadratic dependence on VGS minus VT. Now let me highlight these important parameters. So ID is a quadratic function of VGS minus VT. Now, I think most of us have come up with first with the BJT. If you recall in a BJT, the collector current is an exponential function of VBE. Now, there's an exponential relationship between collector current and the base to emitter voltage in a BJT, and therefore it has got a very high value of transconductance. A small change in VBE will cause a very large change in collector current. Unfortunately, for a MOS transistor, the relationship, even in the strong inversion saturation, the relationship between ID and VGS is not exponential. It is just quadratic, which is a much weaker function compared to a BJT, which has an exponential relationship between VBE and IC. So on this count, the MOSFET really doesn't perform as well as the BJT because it has got just a quadratic relationship between ID and VGS. So we can find out the transconductance GM by differentiating this with respect to VGS, and we will get these three values of three different ways of doing the same thing. Now, look at this. This is the three ways, but this is the most popular expression which people use in general for the transconductance. Now, this, if you know the drain current, if you set the drain current ID from the biasing, you can select the overdrive voltage, VGS minus VT, and this will set the required value of GM as per if GM is part of the specification. So 2ID by VGS minus VT, remember this expression of GM, and you can obtain this expression by differentiating this with respect to VGS. And all the expressions are equivalent. It all depends which parameter you are keeping constant and which are the parameters you are varying. Now RDS, this is the most important thing. RDS, you can obtain as a reciprocal of GDS, which is 1 upon lambda ID VDS. And then if you do this, what you get is 1 upon lambda ID. And then, but the problem is lambda is proportional to 1 by L. And therefore, I'll say that if I say this is this ID, that is, for a given ID, if you want RDS to be large, you have to choose L to be large. You cannot use a smaller channel length devices to get the required value of RDS. And remember the gain expression, it is GM times RDS. If you want high gain, you must have the highest possible value of transconductance and the highest possible value of RDS. And that's the problem here. You cannot use shorter channel length devices to get very high gain. If you want to get high gain, use longer channel length. Now it depends on area. What is the maximum longer channel length that you can use in your design? Because silicon space is expensive. Let's move on. Now this is the comparison between the saturation and triode. Look at this. The transconductance value in the triode region. It is this VDS. And here it is VGS minus VT. And remember, what is the maximum value of VDS that you can have in triode? It is VGS minus VT. And therefore, the maximum transconductance that you get in triode will be the same as you always get in saturation. And hence, saturation is preferred because in saturation, the value of transconductance is always more compared to triode. And similarly, the value of the value of RDS is very small in triode compared to what you get in saturation. And this will be clear when you look at the characteristics also, ID versus VDS. Look, it's if I look at the characteristics ID versus VDS, the characteristics are much more flatter in case of this is ID versus VDS. The characteristics is much more flatter in case of saturation compared to in case of the triode. So in the triode region, the resistance in saturation, and therefore, in order to get high gain, the GM is larger in saturation and the RD is larger, and therefore, for an amplifier, we use saturation. We must ensure that all the transistors must operate in saturation to get the reasonable characteristics. So you have to keep this thing in mind, why we want in a MOSFET to operate in saturation. In triode, only if you want it to realize resistance. That's it. Let's move ahead. Now, there's one more effect, which is called the short channel effect. And the short channel effect will be prevalent when L becomes less than 0.25 micron. And the problem with this effect is the saturation happens when VDS is not more than VGS minus VT. The saturation happens when VDS becomes more than VDS sat. So normally the Ohm's law is followed. The drift velocity is proportional to the electric field. The Ohm's law is valid till 1.5 volt per micron. The problem is this value will be achieved at much lower voltage in advanced technology node. And therefore, when VDS exceeds, let's say, 0.5 volt or so, we always get saturation, irrespective of the fact whether VDS is more than VGS minus VT. This effect is called velocity saturation, and it's prevalent in short channel devices. Short channel devices means devices with less than, let's say, less than 0.25 micron. And so now the value will be different for different technology, but this is a big problem, big problem. Because of this velocity saturation, we are getting saturation at lower voltages of VDS compared to what we get in the long channel devices. And this is one problem that we have. Now, so what happens is, because of this problem, normally, especially for large gate to source voltages, what happens is the device should saturate at this value. But the problem is, and another problem because of this, the formula will also change. So if I incorporate this velocity saturation effect, then my drain current now becomes a linear function of VGS minus VT. It's no longer a quadratic function. So it becomes like, say, poor dependence of ID on VGS minus VT. And what I get, if I take del ID by del VGS, it becomes constant. It doesn't change. So if I say del ID by del VGS, it's become now. So what I get is my transconductance becomes saturated. So I get like a fixed transconductance, although this happens at larger value of VGS, but then the transconductance doesn't rise further because of this velocity saturation. Why? Because of this linear term. It doesn't rise further. It becomes fixed because VD sat is fixed. It is not going to change. And that is the big problem with the MOSFET at the nanoscale. So I'm highlighting that transistor from the analog perspective is really better at the nanoscale because of this velocity saturation problems and many other problems of short channel effects as well. So now, but I think I'll after this I'll close so that you can have a rest, and then we can start with the design of this with the key blocks description after this. Now, the last region for a MOSFET is what's called the weak inversion region. weak inversion, I think the first speaker highlighted leakage power. What is leakage power? It's very interesting. Normally, we assume that when the gate to source voltage is more than the threshold voltage, the transistor is on, and when VGS is less than the threshold voltage, the transistor is off. In reality, it never happens. The transistor voltage, the drain current never becomes exactly zero when VGS becomes lower than the threshold voltage, and this problem is severe when we scale the threshold voltage. See, the problem technologies, in older technologies, we are having supply voltage 5 volts, the threshold voltage 1 volt. But because of low power, we have to scale the supply voltage to 1 volt. Now, the supply voltage is 1 volt. You know the overdrive? Overdrive is VGS, which is VDD, minus VT, the threshold voltage. So once you scale the supply voltage, you have to scale the threshold voltage. And once you scale the threshold voltage, the problem is now you are moving the threshold voltage close to the VG is equal to 0 or close to ground. Now what happens because of this? We assume that there's no drain current flowing when VGS is less than VT. But when we scale the supply voltage, these current, which used to be negligible, started rising exponentially. So any decrease in threshold voltage will exponentially increase this current which is flowing between drain and source. And you can assume it cannot be a drift current. Why? Because the gate to source voltage is less than the threshold voltage, and you cannot have a channel between source and drain. So once you don't have a channel, and the another problem is the channel length is very, very small at the nanoscale. So you can assume this transistors is N plus PN. The MOS transistor starts behaving like a bipolar transistors, and then the relationship between drain current and VGS is no longer quadratic, it's no longer linear, it has become exponential, just like a BJT. So in the weak inversion region, or maybe a sub-threshold region, because in analog we call it a weak inversion region because we extend it slightly beyond threshold as well, as you will come to know shortly. But because of this leakage current which flows between drain and source, when VGS is less than VT, even VGS, when we make VGS equal to 0 also, then also there will be a current flow between drain and source. So today, the transistor is never off. It is either fully on when VGS is more than VT, or it is partially on when VGS is less than VT. And if you have a billion transistors in your mobile phone or in your complex device, and every transistor, which is even not working, is contributing some leakage current, you can yourself gauge the leakage power is an enormous challenge today, which everybody has to face. And there's a lot of research leakage power, which is the problem is the transistor today is never fully off. It is either fully on or it's partially on, thanks to the leakage problem. So in analog, we can exploit this region to do some interesting things because this sub-threshold region or a weak region in some crude form in the analog world, they're quite similar. And so VGS is not exactly less than VT. VGS is close to VT, for we call it a weak inversion region. And in that region, what people have modeled is the drain current is an source voltage. That is the big plus of it, because drain current is an exponential function of this VGS, because the primary mechanism of current flow between drain and source is not drift, it's diffusion. And whenever you have diffusion, you get this exponential relationship. The transconductance GM is very close to what you get in a the BJT. So at that current level, the level of transconductance is quite high. But since the current level ID is very, very small, is very the actual absolute value of the transconductance because of the lower current level will be small, but del ID by del VGS is large, I can say, but the absolute value which we are getting is small. But this region we can exploit because the current level is so low for biomedical applications. This region we can exploit in the IoT node, where we have to go for what's called batteryless electronics. We want the power consumption to be as small as possible. So this weak inversion region, where all the voltages are very, very small, the current is very small. If bandwidth is not an issue, if speed is not a problem, then we can operate at very low current levels. especially when low-speed IoT nodes are concerned, or for biomedical application, or maybe for if maybe in some of the neural networks, if you really want to use it, it's very attractive to cut down the overall power because the circuit is becoming so complex. You cannot accommodate the full neural system, the same chip. You can ensure that the transistors are operating in weak inversion regions, especially for the analog neural networks. It's very attractive, and people had come up with chips which are operating in a weak inversion region and working fine. So I'll conclude with this. Maybe I'll put one or two slides about the importance of this region. So what we have at the topmost, we have the velocity saturated transistor where uh, where you have the absolute value of GM is very large, but the relationship is saturated. The GM cannot go beyond that fixed largest value. So if you want really large GM, then you have to operate it as a velocity saturated device, large value of VGS. But if you want VGS minus VT to be moderate, then you get a quadratic region where normally the analog applications they lie. This is called a strong inversion region, and this is the most attractive region for most of the analog applications where the speed is an important requirement. If speed is not an important requirement, then you can even think of operating in what's called the weak inversion region, where VGS minus VT is very small. You're operating very close to what is called the threshold voltage. So depending on the current levels that you want, if you want the highest current levels and high speed operation, you operate it as velocity saturated. If moderate, operate in the strong inversion region. If you can sacrifice speed, but power is a crucial issue. Speed is not important. You can well decide the weak inversion region and the best of both worlds you get in this strong inversion region where VGS is moderate and VGS minus VT is not large. And that's how between the drain current and VGS is exponential. You have the strong inversion region where large in this, but then of course the level of current is also very large, so it's not really good from a this will give where the speed is not a concern. We can use the weak inversion region, and then so the weak inversion, if you draw boundary you can assume that the transistor has the same characteristics where some saturated, then VT plus 0.5. So between VT for strong inversion, we set the overdrive voltage VGS minus VT around VT will be 0.5 or more than that for the velocity saturated high VGS, and this is for the moderate inversion region will be very, very special. We have to choose the different domains, and accordingly, these boundaries will be available from the model. And then we'll get this boundary VGS equal to VT, where the two are equal. So, but remember, normally we have to use overdrive equal to around 0.2 as a customary thing. Inversion, VGS minus VT will be very, very small, will be around maybe 10 millivolts or maybe less than that. it is going up, or depending on the VGS minus VT value. Is very small. Now, I think, what's the time? The time is 12. Shall we break or for 15 minutes before I'll take this most capacitance?
Yeah, sir,
What
we'll
do you
break.
think? We'll break. I
we'll
think
break.
I think it's a long one. So I'll go through the key blocks. Important thing about the designing of the key blocks, which you have to keep in mind. Okay. Thank you very much for your patience. If you have any questions, you can ask me right now.
So, okay, we'll break for 10 minutes, sir. Around.
All right. Okay,
yeah,
10 minutes
12.
means what's the time? The time, yeah, maybe it's 12:03. So what about, shall I come back at 12:15?
Yeah, 12:15. We'll go 12:15.
12:15 will be. Or
Yeah. Sir, sometimes there is a voice break. Sometimes it happens. Minor, but it happens.
okay. So what shall I do? I'll put the earphone
I don't
properly.
know. Yeah, I don't know. Yeah.
Yeah. Maybe I'll be
Now, yeah. From last 5
hearing
minutes, it was
problems.
a little.
Better. Okay.
In last 5 minutes, it was prominent. Means disturbance was prominent. Yeah. Okay, sir. So take a break. We'll meet at 12:15. We'll see you. Yes.
Having this problem, right? Okay. Thank you. Hello. Shall I start?
Yes, sir. I think we should start.
Okay. Am I audible now?
Yeah, clearly audible. Actually, 95% times you are clearly audible. Sometimes it creates minor voice.
All right. Yeah, it might be because of my sling.
Yeah.
Sorry for that. All right. Yeah, I
Okay,
think
sir.
it's because of that.
It's okay.
All right. All right. Okay. All
Okay.
right. Okay, so I just went through the IV characteristics till now. So what I'll do is I'll quickly go through the CV, because you have to understand the different capacitances of a MOS transistor. Because once you have understood the capacitance, only then we'll talk about the frequency response in a more effective fashion. So if you look at the MOS transistor, you have a gate capacitance now. Now the problem is the top terminal is gate and the bottom is the channel. So the gate capacitance is basically divided between gate and source and gate and drain. And this is like a parallel plate capacitance, which is a voltage independent capacitance. And you have, because of the lateral diffusion, you have an overlap capacitance also between the gate and the drain and the gate and the source. So you have this is also voltage independent capacitance. And then you have a source bulk junction, and then you have a drain bulk junction. And then this will give you a voltage dependent drain to bulk capacitance and the source to bulk capacitance. So you and a voltage independent component of capacitance. Now, the important thing which is important for an analog designer is the values of these capacitance in different regions. Now, for analog designer, the most important region is the saturation region. So we have to really confine ourselves for the and what happens is the gate to source capacitance. Now, the gate to source capacitance is because the channel is confined towards the source. There's no channel at the drain end, and therefore the gate to source capacitance is predominant in case of saturation. That is, in saturation, the gate to source capacitance is almost 2 by 3 times WLCox, where you all know Cox is the oxide capacitance per unit area. You multiply it by W into L, and then you can derive this relationship in saturation. It will come out to be 2 by 3 WLCox into WCOV. Whereas the gate to drain capacitance in the saturation region is just equal to the overlap capacitance. So the gate to drain capacitance value is much smaller compared to the gate to source capacitance in saturation. This is the most important message that you have. And then, of course, you have the voltage dependent drain to bulk capacitance and the source to bulk capacitance. And now, since the drain voltage is larger, so the value of the drain capacitance and the source capacitance will depend on the voltages of the drain and the source. And since they are voltage dependent, so that the values will be different. But the most, because the gate capacitance is the predominant capacitance, so you have to keep this thing in mind that the gate to source capacitance is much larger. The value is 2 by 3 WLCox plus a minor component coming from the overlap, whereas the gate to drain capacitance is very small compared to the gate to source capacitance. And this important message has to be kept in mind for an analog design, because this will help you out in this. So now what I'll do is we have computed the value of GM, we have computed the value of GDS, we have computed the value of GMB, and then we can use these three components to arrive at the total. So the total drain current in the small signal model will have three components. One component is contributed by the gate to source, GM times VGS, which is the dependence on ID on VGS. Then you have a second component coming from RO, which is your GDS component, how the drain current relates to VDS. And then you have another current source coming up, the dependence of the drain current on the bulk to source voltage. And then you can add the different capacitance that you have, the gate to drain capacitance, which is a very small capacitance in saturation, the gate to source capacitance, and then you have the source to bulk voltage dependent capacitance and the drain to bulk capacitance. And then you have a gate to bulk capacitance when there is no channels, especially in the weak inversion region, you have a top plate as the gate plate and the bottom plate as the bulk because there is two channel. So during subthreshold and weak inversion, you have to take into account the grade to bulk capacitance. Whereas in saturation and in the triad region, this capacitance is zero because the top plate is the gate and the bottom plate is the channel, and the channel shields the bulk completely. Now, so these are the different parameters in different regions, the drain current, the transconductance, and the RDS. So I again told you, again reiterate, if you want really high speed and the power, you're not bothered about the power, then you have to operate in the velocity saturated region. For typical moderate applications, you have to have this strong inversion saturation region. And then for very ultra low power applications, especially for the IoT or the neural network or biomedical, you can think about even the weak inversion region. Now, let's move ahead. Now, what I'll do is I'll concentrate on the design aspects of the key analog building blocks. The whole idea is once you understand these building block operations, then you can identify these blocks in complex designs, and then carry out handle the complex design in a much more effective fashion. So this slide I already told you, I don't want to repeat it. Now, before moving further, again, I reiterate, this is a basic MOS transistor, and then biased by an ideal current source having an infinite resistance. What can be the maximum gain this amplifier can offer? Because we must be aware the limits of the maximum gain that a single transistor amplifier can give. And because if we carry out this small signal analysis, the whole idea is we can replace each transistor by its small signal model, which I had discussed till now. And then maybe a very simplified form of that model. And the simplification we'll learn through experience, whether we have to include the resistance in the model or not, or we can even skip the resistance. In some cases, you have to include the resistance RDS. So we have to have an idea how to replace the MOS transistor which we have in our design by the most simplest model to start with, and then carry out the computation. And then we'll make the model slightly more and more complex so that we can converge, we can't sacrifice that much of accuracy. So that's the whole idea. So remember, in this PMOS analog design, every transistor has to be replaced by its small signal model before carrying out the analysis. That's the whole idea. So what's the maximum voltage gain that you can get? So if you look into the basic circuit, you have a current source GM VGS, and then in parallel you have the resistance RO, which is RDS, and in parallel you have the infinite resistance that will not play a role, and therefore the gain will be just GM times RDS. Now GM, you all know, is 2ID upon VGS, and RDS is 1 upon lambda ID. So the final expression that you are getting is this. Now, where lambda is equal to 1 by L, so approximately I'll say that the gain expression will be like 2L divided by VGS minus VT, where VGS minus VT is the overdrive voltage. So this is the typical thing which we are getting, where VGS minus VT is the typical overdrive voltage. Now, in order to get a high gain, what we have to do is we have to choose a large L, that's the requirement, and a low overdrive voltage. There are two requirements which you can take it here. If you want gain, if the gain is the most important parameters that you have to choose a longer length transistor. You cannot choose a minimum length transistor for this transistor, because I want to maximize the gain. I have to choose a longer length for this transistor. I cannot choose a smaller length because the RDS will depend on the length, because RDS is proportional to the length. The longer the length, longer will be the RDS. So the easiest way to maximize the gain is choose a longer length transistor, and secondly, choose a small value of the overdrive. So these are the two conditions which I'm having to maximize the gain. So the conditions are: never use minimum length transistors if high gain is required to increase the value of RDS. If minimum length is chosen for the bandwidth consideration, If at all you have to choose a minimum length, you don't have a choice. Whenever, if you are forced to choose a minimum length, then you have to use some gain boosting techniques to achieve the required gain. For instance, I'll tell you now very shortly, maybe you can use gain boosting, other techniques, maybe you can use cascade. So you have to go for other techniques if you're forced to choose the shortest channel length. The easiest way is, if gain is the most important parameter, never ever choose the minimum transistor length as the length of the transistor. You have to choose longer channel length. Only then the required gain can be achieved. And secondly, you have to choose a smaller overdrive voltage, VGS minus VT, per the expression, to get the higher value of transconductance while operating in this strong inversion. That's the most powerful region. So that's the thing that you need for a high gain. High gain, longer length, and low VGS minus VT. That's the requirement. But if you look into it from a bandwidth perspective, the requirement is reversed. So things are at loggerheads. For the gain, the requirement is different. For bandwidth, it's just the opposite. For bandwidth, longer length means longer W. The bigger area. Bigger area means more capacitance. More capacitance means poor bandwidth performance. It will be clear from the next slide where we are plotting this unity current gain frequency FT for a given design. And what is clear from this, FT is proportional to this VGS minus VT squared. It's just the reverse, divided by L squared. So in this, what it says is that in order to get the highest possible value of this unity gain frequency, I choose a large value of VGS minus VT and a small value of L. So need higher VGS minus, it's just the opposite to gain. So you can yourself gauge now the trade-offs. It all depends on the specifications. We can't get a high gain or a high bandwidth. If you want bandwidth is the most important criteria, then you have to look for other methods rather than just choosing a longer length device. You have to use maybe cascade and some other gain boosting techniques, which will ensure that you can keep the length minimum and is still able to achieve the required specifications. So these are the important considerations that you have in your design. Even if you don't want to go into this detail, you can just think about longer length transistor means proportionally more W to get the required W/L ratio for a given current, and then more area, W into L, and capacitance depend on the area. So higher capacitance means, of course, the lower bandwidth. Let's move ahead. So in a nutshell, for high gain, you need a low value of VGS, typically 0.2, and high L. Whereas for high speed, you know high value of VGS, normally 0.5, edge of velocity saturation, and then low. This is the requirement. And loggerhead. You have to be very careful about it. Now, I'll start with a very simple way of this current sink. Current sink is very popular circuit in current sinks, where you connect a fixed voltage at the gate, and then this is responsible for the biasing current, I. Now, the current sink means that the resistance will be high. And resistance can only be high if you operate in this saturation region, because the characteristics are much more flatter, and the resistance is given by 1 upon lambda I, because RDS. You all know this, 1 upon lambda I. The relationship is RDS, so it is. Now, the problem is the lambda is inversely proportional to L. So small lambda results in higher R naught. So remember, if you want to design a good quality current sink, you should never use minimum size transistor. If I want to carry out a small signal analysis, this is ground, and therefore the gate is at a fixed voltage. So as for the small signal analysis, I have to keep it at ground. Now, since both are at ground, VG is equal to 0, so this will vanish. From drain to source, you get only a resistance R naught, which is 1 by lambda I. So small lambda is ensured by choosing non-minimal channel length. So for biasing circuit, especially in the current sources and current sink, you can write it down. It's very important. Never ever use minimum channel length, because minimum channel length will give you lower value of R naught. For a good quality current sink, the output resistance should be as large as possible, so that I want an ideal current source ideally should have an infinite resistance. How to get a higher resistance? Choose non-minimal channel length. But of course, you cannot have a very long channel, and then because then the area budget will come into picture. You cannot exceed the area allocated to the current thing. Otherwise, the overall area will go up. So as a designer, you have to have a trade-offs, a lot of things, a lot of things you have to optimize. So depending on the area that has been allowed, you have to choose a longer length because longer length will lead to longer W to get the required W by L. This has to be kept in mind. And the similar thing is valid for a current source. Normally, the current source is towards the VDD side, and they have to be they have to be of PMOS type, and the current six is close to the ground. That to be of NMOS type. And remember this. So whenever you want to have a current source, this scenario again the same thing. How it's good for a PMOS also. You have to choose a long channel length to ensure the large values of of the resistance, because ideally we want an ideal current source the resistance should be infinite. Let's move ahead. Now I'll start with very basic single transistor amplifier with resistive load to just communicate with you the basic stuff that I really want. Now the most important thing here is I've already told you about the gain, but in this the load is RD, so that will limit the gain. It will be minus GM times RD because the resistance RO will be much larger. And so the gain will go down because of the limited value of the load resistance. So what is the output swing is another very important parameter. And the current, the biasing current will depend on the power budget, as you all know. So a V out max for this circuit, that's the maximum voltage I can have is in this circuit is when the maximum voltage is I can go up to, because if the current becomes zero, I can go up to virtually a VDD. But the minimum voltage will depend on this transistor should operate in saturation. This transistor must operate in saturation all the time. And for this transistor to operate in saturation all the time, it means that the value VDS should be at least more than VGS minus VT. So therefore, the V out minimum can be V in minus VT, and therefore the output swing will be the difference of V out maximum and V out minimum. That is the output swing that you can have in this circuit. That is the maximum thing that you can have in this circuit. But in reality, you cannot achieve that swing because of the other issues that you have. Now, the next thing is this is your diode connected load. In a diode connected load, this is like an active load where I am realizing the load. We have replaced the load resistance by an active diode connected. Diode connected transistor means I have shorted its gate and the drain terminal. Now, what I have done is what I have achieved through this, the gate to source voltage will be the same as the drain to source voltage. Now, by doing this, by just putting this drain to source the same as gate to source voltage, one thing I have done is if I compute the resistance of this, the resistance of this will come out to be 1 by GM. And I'll show you in the next slide what is the value of this resistance. This resistance will be 1 upon GM that this will give. And then for this M1 transistor, the the transconductance will be GM1, and therefore if I assume this to be negligible, GMB2 approximately will be minus GM1 upon GM2. Now the problem with this diode connected load circuit is that it gives you very low value of gain because GM1 and GM2, the two are forming a series circuit. Both will be having the same current, and therefore GM1 and GM2 will be very close to each other, and therefore this circuit will not be able to will not be able to give me a very large gain. But the linearity aspect is good. Why? Because the gain depends on the ratio. So whatever changes will happen in GM1, most probably the same changes will happen in GM2. And therefore, since the gain depends on the ratios of two same quantities, and therefore most probably the linearity will be better compared to other circuits. Now, V out minimum can be just V in minus VT, because to ensure that transistor M1 will operate always in saturation to get the required value of GM1, and then V out max. Now, for this transistor to be on, at least the VGS should be more than VT, So it will be, you'll get that V out max, and therefore the output swing will be the difference of V out max and V out min. So in this case, you'll see that I'm getting a reasonable value of V out, the output swing. So for a given circuit, you should be able to compute the drain current. You should be able to compute the voltage gain, and you have to compute the output swing, as well as I'll let you know for one circuit how to compute its bandwidth. Now, for a diode connected load, as I told you already, the basic thing is the gate to source voltage must be the same as the drain to source voltage. And if I carry out this small signal analysis, I can, because this voltage, because the controlling voltage, this is VDS or V1, which is the same, the controlling voltage is V1, and the voltage across this current source is also V1. And therefore, I can replace this current source by 1 upon GM. And therefore, this 1 upon GM is large, and therefore 1 upon GM will be a very small resistance. If that small resistance will come in parallel with R0, which is a large resistance, the overall resistance will be 1 upon GM if I neglect GMB. And therefore, Vx by Ix will be 1 upon GM. So remember forever, if I have a diode connected load, it offers very low resistance, 1 by GM. So whenever you come across diode connected load, one thing is there, it will give you more linearity. The negative point is the resistance is very small, and therefore the gain that the diode connected load will provide is very, very small. So it depends. If you want linearity, go for diode connected load. If you want reasonable swing, go for diode connected load. Otherwise, don't go. Now, a better option will be a current source load. Now, in this current source load, what happens is, of course, the source voltage is fixed. The gate voltage is also fixed. So by looking at this, you can find out the load is the current source load. So what I'm discussing is a single transfer amplifier. You have a driver which is M1, and then you have a load which is a current source load. Now, in the current source load, the gate voltage is fixed as well as the source voltage is fixed. So it means that the gate to source voltage will be zero, because all the fixed voltages will be shorted. And therefore, what happens is this GMVGS, if I use the most approximate model, will be zero, and I end up only with the resistance R0. So therefore, this M2 will offer a resistance RO2. This will offer a resistance RO1. So if I carry out a small signal analysis, my overall resistance will be RO1 in parallel with RO2, and the voltage gain will be minus GM1 R1 in parallel with RO2. If I want to find out V out max will be VDD minus the drop across this, and that will be VGS minus VT to keep it in saturation, M2, so that the resistance continues to be RO2, and then V out minimum will be V in minus VT, and therefore the difference output swing will be V out max minus V out min. You have to find out through this. Now, if I can get a good swing if I replace this load by a triode load. But the problem is the value of the ohmic load, the resistance will be much smaller. So if I can sacrifice gain, I can use a triode load. And you know that in a triode load, the VDS value is very small. In the linear mode, the drain to source voltage is very small. And therefore, my V out max will be larger if I replace this current source load by a triode load. But the negative point is the gain will become smaller. Why the gain becomes smaller? Because the resistance of the triode load is much smaller compared to the resistance in saturation. So if I can sacrifice gain, I'll get more output swing. So output swing and gain is also at loggerheads. If I use a current source load, I'll get more gain because RO1 in parallel with RO2. If I replace it by a triode load, because this triode load now VDS is very small for the triode load, so the output voltage maximum will be VDD minus small VDS, which is very close to zero. It will be the output max will be close to VDD. But in this case, the output swing for a current source load will be poor because this is this is a smaller value compared to if I replace this load by triode, but then you have to sacrifice the gain. So what I'm saying is the gain and the output swing is also at loggerhead. So you have to really careful match depending on the requirement. You have to choose the proper load so as to satisfy your specification. Whether your output swing is important, whether your gain is important, whether your bandwidth is important, based on that, you have to decide the topology which will be most right for your design. Now, if you want a still higher gain, I can use the traditional CMOS inverter. And why I can get a larger gain, although it has many other hiccups, because now the input is applied both to PMOS and MOS. It's an active, the load is also active, just like a driver. And therefore, the effective GM now will be GM1 plus GM2, and this resistance remains the same. So this will give you an even higher gain, but designing this is a challenge. And why it's a challenge? Because the supply voltage VDD will be VGS2 plus VGS1. So if I add VGS1 plus VGS2, I'll end up in VDD. And if there occurs any variation in the supply voltage, it will be nightmarish. VGS1 and VGS2 both will be affected, and therefore there'll be a big problem to control the circuit operation. So what we get is a very poor power supply rejection ratio. That is, the output voltage will be dramatically affected if there occurs a change in the supply voltage. So this circuit is highly prone to the supply voltage variation. Now, this is another interesting topology where you have you use two resistors RD and RS with source degeneration. And the important thing about this topology is the gain is a function of the resistance ratio. So it's good linearity, but at the cost of gain, because realizing large resistance will take a large amount of area. But of course, the linearity is good. So if you want a linearity in your design, that you can't sacrifice, then you have to see to it that your gain depends on some of the ratios of parameters, ratios of resistance, ratio of transconductance, where the errors will get eliminated rather than the absolute value, just like a current source load. So if you can sacrifice gain, you can get linearity. If you can sacrifice gain, you get a better output swing. So it all depends on what is your important parameters that you want to optimize. Let's move ahead. Now, this is the design of another important component called source follower, a voltage buffer. Now, in this voltage buffer, what you have is you take the output from the source rather than from the drain. Normally, the output is taken from the drain, but in this case, the output is taken from the source. And therefore, there is just a VGS displacement between the output and the input. Now, the most important characteristics of this is the output is very, very close to input, very close to 1. That's the output follows the input. So it's a voltage buffer. Now, the important characteristics of this is it has got a high input impedance, but a more important one, it has got a low output impedance. Now, this low output impedance will help you in driving a low resistive load, and that's very interesting. So at times you need it when you have to drive the low output impedance loads, which you can't do it using a normal amplifier, because if you put the direct low impedance loads in the normal amplifier, the gain of the amplifier dramatically goes down. So why not insert a voltage buffer to drive it, and this will keep the gain intact, because then this is a very important property of the source forward that you all know. Then the second one is this current buffer. Now, current buffer is common gate topology. Now, in this, the input is applied to the source. So, characteristics of this topology is very interesting. It's like a current buffer. The output current, because the output current is the same as the input current, and the input resistance, if I compute, is very small. Normally, the input resistance is very large for the other topologies because the input is fed at the gate, but since the input is fed at the source, and it has got a very low value of input resistance like a current amplifier, and then the output current is the same as the input current. Now, now moving on to a very interesting topology, because you can combine this common gate stage and you can replace this input by an active device. And that active device is your nothing but a common stage. So a cascode stage is a combination of a common source stage and a common gate stage, where I have replaced the input to a common gate by a common source stage. And the big advantage of this combination is that this combination will give you a very high gain at V out, because if you compute the output resistance of this combination, the output resistance is very high, but the overall output resistance will be lower because that output resistance will come in parallel with RD, and therefore the overall output resistance will go down. But the beauty of this structure is it gives you a very high value of output resistance. And remember, if the output resistance can be high, it's possible to get very high gain. But you can't get everything for free, because now two transistors are between Vout and ground. If there are two transistors in between Vout and ground, the swing at the output will be affected. So in cascode, although it gives you very high gain, as you'll be coming to know shortly, the output swing will be much lower compared to, let's say, whenever you have a single transistor between the output and ground. So now this is the real cascode where what I have done is that RD I have replaced, because RD is a nuisance. It was trying to, because when I put RD will come in parallel, and then the overall gain goes down. So if I really want to get a high gain from a cascode stage, I have to realize RD not through a normal discrete transistor, but through a current source, because current source will give me a very high value of resistance. Now, and that too, so what I have is this combination will give me a high output resistance R out, and then the gain will be equal to GM1, the gain of this transistor, plus into the high RR, and therefore the overall gain will be very high. So in a cascode, the overall gain is very high. So if you want very high gain, combine common source stage with common gate stage. So if the gain is the number one requirement, and you are ready to pay the price in terms of the output swing, then the cascode stage is very attractive. And the practical realization of cascode stage is this: you have the current source is realized by these two series connected transistors, whereas this two series connected transistor now is over here will be, so we have two transistors between Vout and ground and two transistors between Vout. Is very high because the overall resistance will be R out 2, which is a large resistance, in parallel with the large resistance R out 1. So I think the two very large resistance will not make the R out smaller. It will be, of course, 1/2, but that 1/2 is not a big factor because these individuals R out 1 and R out 2 is very large. And then this will come in the GM1 will be there. So this topology will give you a very high voltage gain. But the problem with this topology is the Vout max will be VDD minus the overdrive of port. Two overdrives will be coming rather than one. Similarly, from Vout to ground, two overdrives are coming. And therefore, the problem with this is the overdrive voltage. This is like the output showing Vout max minus Vout min will be much smaller. And therefore, you cannot use this circuit where output swing is very important. Or maybe you have to put another circuit after this, which will have only one transistor between Vout and VDD and between Vout and ground that will be able to give you the required voltage swing. Because the problem with this cascode is it gives you very high gain, but then you have to sacrifice the output swing, which is which is also an important parameters as per the specifications. The single transistors, the amplifiers, and of course the cascode, how you can increase the gain. There are other ways of doing it, but cascode is a very popular way. You have another gain boosting techniques. I don't have the time to really touch upon those techniques within the limited time that I'm having. Now, another very important block, which is because you have to set the different currents in a complex, maybe an operational amplifier or the building block. So current mirror is the most important key block for doing that. Now, remember, for any analog circuit, you must have a reference current or a reference voltage, normally a band gap reference. Now, this reference current should be immune to any process voltage and temperature variations. Now, the whole idea is why you should have one reference generator on the chip for analog, and that reference generator should generate the current, and all the other currents will be derived from this reference. Now, the current mirror will do just that job. You generate a reference current through a reference generator, and then the current mirror will distribute this current throughout the whole chip. This is the great job that the current mirror performs. Now, what the current mirror does, the reference current is set by the reference generator, and then this will redistribute the current through this very interesting circuit. Now, this copy circuit is basically a diode connected MOS transistor. What you are doing, what this diode connected MOS transistor does, from a current, it generates a voltage. So it's a very interesting circuit. You generate VGS. From a given reference current, it will generate VGS, and this VGS will apply here, And then from this VGS, this output is I out is generated. So if I keep the W by L by 2 is the same as W by L1, then I out will be exactly equal to I reference. And this I out will be connected to my analog circuit through which my biasing current is flowing. So basically, if I make W by L2 twice compared to W by L1, then my I out would be twice compared to I reference. And I can just move I reference anywhere to the PMOS side, I can just move it around with the help of this current mirror anywhere in the chip. I can move it to the PMOS side, I can move it to the NMOS side. So this is very interesting. But it's very important for this mirroring to happen that the voltage Vy should be close to Vx. Otherwise, VDS2 will be different than VDS1. And because of channel and modulation effect, I out will be different from I reference. So for proper operation of the current mirror, it must be ensured that X and Y will be close to each other as possible to ensure that I out will be the same as I reference. If you cannot do it, then we have a more complex current mirror that will help you in that endeavor. And that complex current mirror is the cascode current mirror. Now, what is the advantage of a cascode current mirror? Is let's say this is the circuit which is connected to node P. You cannot really, can have a very high value of V out, which is quite more than Vx. Now the problem is if Vx and Vp are radically different, then in that case, what happens is that the I out will not be the same as I reference. To combat that, these two extra transistors are inserted to realize what's called a cascode current mirror. In that, what really happens is these two transistors will ensure that the Vx and Vy will remain very close to each other. Whatever changes happens here will be absorbed by the VDS3 drop. The Vy will be very close to Vx. And by ensuring that the I out will remain close to I reference, despite the fact that Vp will be quite higher compared to Vx. So this cascode current mirrors will be effective if you really want to maintain I out is equal to I reference in cases where Vp will be different than Vx. Let's move ahead. Now, in different circuits, I have not shown the biasing, but biasing is very important for the current source load as well as for a simple amplifier. Remember, you have to operate this transistor. For proper operation, the driver transistors and the load transistor must be properly biased. And you must have elaborate biasing strategies for different circuits. Biasing is basically setting the different currents. You have to use references, current mirrors, current sources to ensure proper biasing of the circuit, proper operating point to ensure that transistor M1 should always remain in saturation, come what may, so that I could get the required value of GM. Because if the transfer goes into tryout region or some other region, the GM, the gain will be dramatically affected. And therefore, biasing is one of the most important parts. And therefore, you must ensure that your circuit should be properly biased. Now, these biasing currents will help you because all the terminal voltages and currents will depend on this biasing values, because all these small signal parameters like GM and RDS will be extracted only once you set the biasing currents. The biasing current is very important in setting the small signal parameters, which will then help you in computing all the other parameters like the gain, the bandwidth, and the other things. Now, let's move ahead and concentrate on the most important part of the signal transfer amplifiers and the cascade amplifiers, and that is your differential amplifier. Now, you must be wondering, differential amplifier means I'm using two identical blocks rather than one. The circuit complexity just becomes twice, but we are doing it for a purpose. Now, a single-ended output is with respect to, let's say, some reference, you are moving around that. And then the output swing will be, the maximum will be Vm and the minimum will be minus Vm. So the output signal swing is 2 Vm. Whereas in case of differential output again is moving around a common mode level. So Then if the differential output will be Vx minus Vy. It is not with respect to any reference, it's with respect to the two nodes. So the differential output will be Vx minus Vy. And if I take this differential output Vx minus Vy, it will be basically, because Vx is Vm cos omega t and Vy will be minus Vm cos omega t. And therefore, if I take the difference, it will be 2Vm cos omega t. And therefore, the differential output signal swing will be 4Vm. This is very, very important. A differential amplifier will give you twice the output swing compared to a normal amplifier. So that's a one of the very important property of a differential amplifier is it gives you double the swing as compared to a single-ended amplifier which you have studied till now, because the output one is going up, the input one is going down, so the difference is twice, and a differential swing is twice compared to the common single-ended swing. That is very important attribute. The second most important attribute is, since you are taking the difference, the input is differential and the output is also differential. So any noise coming will be coming from the supply side, or if you have, then this supply side noise will affect both Vx and Vy equally, and therefore these differential circuits are more immune to supply voltage variations or noise compared to the single-ended circuit. Although you need twice the circuit complexity for differential compared to a normal. Another very important factor here is, if I keep it this differential amplifier like this, then the problem will be, now the input will be having a small signal component plus a common mode component around which it's varying. Now this common mode voltage can go up and down. If the common mode voltage goes up and down, the drain current of this branch and this branch will be affected. And if the drain current of this branch will be affected, then the transconductance will be affected and the gain will be affected. So the problem is, if I take this basic circuit is highly prone to the problem of variable gain depending on the value of the common mode input. Therefore, the common mode, all the important characteristics of the bias currents are dependent on the common mode level. We don't want that. In order to overcome this problem, we have to introduce one current source that is available here. This current source will make this differential amplifier immune to the common mode changes in the voltage at the input. And how does it ensure that? If we assume this to be an ideal current source, then what really happens is, if the input voltage V in common mode will try to rise, as well as this voltage, because the common mode voltage, both voltage will try to go up. And what happens? The current here cannot change, it's ISS. So we have to ensure the V in common mode is adjusted such that if I assume all the two branches to be identical, ISS by 2 will flow here and ISS by 2 will flow here, so that if I have the resistance is identical, if the common mode signal comes in, there is no differential mode signal, V out 1 will be the same as V out 2, and therefore the differential mode signal will be, differential mode output will be 0. So if there occurs any increase or decrease of common mode signal here, that will not going to affect the current, because the sum of the current will be ISS. So this insertion of ISS will definitely going to help in ensuring that that the common mode input at the input will not affect the performance of a differential amplifier. And this current source in CMOS form will be realized with the help of this current sink, which must operate in saturation, so that the current should not be affected. And we can always find out its voltage ranges, so that we can get the required values. Now, the important message here is, this differential amplifier will give you the same gain as a single transistor amplifier, but it will operate on differential input. It will be having a good property to combat noise. It has a large output swing, twice that of a normal amplifier. Now, there are three different types of MOS differential amplifier, basic types. Again, just like single transistors, you can have a diode connected load, and you get the same expression if you want to find out the differential mode gain. The output voltage is differential, it is this. The input voltage is also differential, V in 1 minus V in 2. That's a differential mode gain. Now, for the current source load, the gain will be larger, R on plus ROP. And then you have an OTA where you are having a current mirror load. So the load can be of diode connected, it can be of current source, it can be of even current mirror. So there are three different types of load available. And based on that, now the important thing is the output here is single-ended, although the input is differential. So this is like an operational transconductor. And under some situation, you need to have a single-ended output. And this circuit is very effective to get the required gain which you are getting for a differential amplifier, even at the single-ended. So single-ended gain will be having the same value that you are getting for a differential amplifier. The only difference is here the input is differential and the output is single-ended, and still you are able to get the required gain. If you want a single-ended output, you can use a current mirror load. If you want a large gain with a MOS differential amplifier, you can use a current source load, and the gain of the current source load and this will be exactly the same. Output is also differential, the input is differential. But if you want more linearity, then you go for the diode connector load, where the gain is smaller, but then the ratios are there for more linearity. Now the important thing is that if you want higher gain than what you are getting here, then you can always use cascode. So you can have a cascode differential amplifier where rather than one branches, you can have two branches. And then with the help of only single stage, you are able to get the required gain. So what I intend to do is, because maybe if whatever time I'm having, I'll give you an idea about how you can design this cascode differential amplifier, because rather if you really want high gain, you can use a cascode differential amp. You can use a normal differential amplifier, and you can have two stages of this differential amplifier, or maybe a normal amplifier plus a single transistor amplifier, or you can have a cascode differential amplifier followed by a normal single transistor amplifier. Now, so basically you can have a two-stage amplifier, or you can have a single-stage amplifier. So this is a single-stage amplifier. The problem with this single-stage amplifier is you'll not be able to get the required swing, because the swing will be smaller compared to, because there are two transistors between the output and supply voltage and the output and the ground. There are even three transistors, so the swing will be effective. Now, so that is the problem with the cascode. But but the advantage is you can get the required gain with only one stage. That is difficult to get in two stages at a time. But then if you can sacrifice the swing. Now, before taking up this thing further, I'll just a slight interruption, because frequency response is also a very important parameter, and how to compute the frequency response on the bandwidth of a normal CMOS amplifier. Now, this is I have taken for a common source amplifier. In a common source amplifier, the easiest way to compute the bandwidth is you have to find out the location of a dominant pole. Now, every node, like for instance, this node, will have a capacitance connected to it as well as the resistance. So the resistance will be Rs, and the capacitance will be some combination of CGS and CGD, which, if you know by Miller effect, the overall capacitance at this node will be CGS plus gain times 1 plus gain times CGD. So for every node, you have to, through inspection, you have to find out what is the gain value at this point, and what is the value of capacitance at this node, and what is the value of the resistance at this node. So you can find out for this. Similarly, you can find out for the output node, what is the value of resistance and what is the value of the capacitance. Now, based on the value of the resistance and capacitance, you will get what's called 1 upon RC. Now, the minimum value of 1 upon RC will be the dominant pole. So we have to avoid that a node having large resistance and large capacitance will give you the dominant pole. So in a given circuit, even through inspection, you can find out what are the nodes available, and what is the approximate capacitance of those nodes, and what is the approximate resistance of that node for a given technology that you're having. And based on that, you can find out which node is most likely to offer you the dominant pole, because that dominant pole will decide the bandwidth. For instance, in this case, if I'm using for, let's say, biomedical application, the RS is very high, and then CGS, you all know, is 2 by 3 C ox W into L. It's a high capacitance. And then this is 1 plus gain times CGD. So this also becomes a multiplying effect. So it's very obvious that in this case, if RS is high, this node X will give you a dominant pole. And this node Y, if I assume there's no load capacitance here, will not give you the dominant pole. Now, if there is a load capacitance and it's very high, then of course the output node will give you the dominant pole. But in this case, if I'm assuming that there is no load capacitance connected, then this will give you the dominant pole. Of course, you have to carry out the analysis and find out the different values of the capacitance that you are having and the resistances of different nodes, and then predict which one is most likely. So by inspection, you can find out the bandwidth or the location of the dominant pole of a given circuit, and that will help you in predicting which circuit will give you a higher bandwidth compared to the other circuit. The mantra is to ensure that a highly capacitive node should not have a high resistance. You can to ensure that that node should not contribute towards the dominant pole and hence the bandwidth. So this is very important. So in this case, if you have a high capacitive load, then for instance, in this circuit, if I assume that this load capacitance is dominating, then this will provide the required um, uh, the required dominant pole. So the gain is, in this case, is GM times RDS, and I'm assuming that the capacitive load is the dominating capacitance. In that case, the bandwidth will be equal to the resistance here, which is RDS, and the capacitance is high, and the bandwidth will be 1 upon 2 pi RDS-CL. The gain of the circuit, you all know, is GM RDS, because the current source is ideal. You can find out this gain bandwidth product, GM upon 2 pi CL. So remember that if you want to keep this gain bandwidth product high, you must have a higher value of GM, and of course the low value of the load capacitance. And remember, for a single transistor, single capacitive circuit that you have here, there's only a single pole. A single pole means the maximum phase that you can have is minus 90. And therefore the system will always be stable, because a single pole system will give you a phase margin of around 90 degrees, which is always stable. And hence, if you have a single dominant pole or a single pole in the system here, then, or maybe the other pole is at a much higher frequency, then of course the system will be stable, because you are able to get the required value of the phase margin, which is around 60 degrees that you want. So the important thing is, for a gain bandwidth product, the capacitance is playing a role, and all the capacitance except the load capacitance, they will depend on the W into L. So whenever you increase the W by L ratio to get a higher gain somewhere, remember that you are increasing the value of the capacitances at those nodes where that transistor is connected. So W into L will decide the capacitance. So whenever you are increasing the W by L ratios, you are paying in terms of higher capacitance and lower bandwidth. That has to be kept in mind. Now, before moving to the final design phase, one another aspect is the thermal noise. And thermal noise is a very important part, and every resistance will contribute toward thermal noise. And the value is this is the square thermal noise is 4 kTr. And every transistor has got a channel resistance and will also contribute towards the thermal noise. Now, one another noise which is very predominant in the MOS world is called the flicker noise, and that's active at low frequency. Now, the problem is, MOS is a peripheral device, so the drain current flows very close to the interface between the silicon dioxide, and then there is a lot of traps in the silicon dioxide, a lot of defects, and these traps will trap the electrons moving from source to drain, and at times they will release the electrons. It's a random phenomenon. So some electrons, more electrons are picked up, or sometimes more electrons are released, and therefore the drain current is variable because of this flicker that is there. And this phenomenon is very active at low frequency, and the noise contribution is is 1 by F, and then for a larger device, luckily WIL can be proven that this flicker noise will be lowered. So if you want to reduce the flicker noise, and if you are operating, let's say, in the biomedical domain, where, or the low frequency domain, the IoT world, the flicker noise will play the most important role. So if you really want to create low noise circuits, you have to ensure and operating at ultra low frequencies in the IoT domain as well as in the biomedical domain, the flicker noise is the biggest nuisance. So two things you have to keep in mind. You have to keep WIL ratios very large. So, and I think this the input device, the differential pair, really contributes toward the big noise in this respect because it's at the input stage. And the problem is the W into L. If you have large transistors at the input stage, then those transistors will contribute less towards the flicker noise because the flicker noise is inversely proportional to the area W into L, and that can be proven. And then, of course, frequency is not under your control. It depends on the application. One another aspect is people have found that in PMOS, the flicker noise, the K constant for PMOS is much lower compared to the NMOS. So flicker noise is much less in PMOS compared to NMOS. If you want to design low noise circuit, it's better to design the input crucial stage, differential stage, as PMOS rather than NMOS. So if you want to design low noise amplifier, it's better to use PMOS because the flicker noise component will be lower in PMOS compared to NMOS in the bio, and choose bigger areas for those transistors so that the flicker noise remains a limit, which is very, very crucial for biomedical applications and in the IoT node. And so what's the strategy, how to compute the noise? So every transistor will contribute towards both flicker noise as well as the thermal noise. And for every transistor, you have to find out the output noise contributed by that transistor. So wherever transistor is located, you have to replace that transistor by a flicker noise component as well as the thermal noise component, and then find out the corresponding output voltage because of these components, and that will be the final output voltage square. That's the total noise of the circuit. So you can apply the principle of superposition by assuming every transistor as a source of both thermal noise and flicker noise, find out the corresponding noise, find out the gain from that point to the output, find out the overall output noise which that transistor generates, do it for all the transistors, carry out the summation, and then divide it by the gain square. That will be the input referred noise. So that will be the input referred noise. Every transistor will be the source of both flicker noise as well as thermal noise. Remember, and then you have to take that thing as the transistor is acting alone, find out the total overall noise contribution by that transistor at the output, take the gain square and refer it back to the input. Now, it's very obvious if the transistor is lying very close to the input, and then I have to multiply that its noise contribution by the gain square till I move to the output. And then again, if I divide it by the gain square, it means that transistors which are lying close to the output, they will not contribute much noise because whatever noise they are contributing, the gain from that point to the output will not be much. And then those noises will be divided by the gain square. Then I refer it to the input noise because normally the noise is referred to the input. Therefore, what is happening is that the input stages are contributing more noise because whatever noise they are contributing, that is multiplied by the gain square and then divided by the gain square again while referring it to the input. Whereas the devices which are close to the output, for that devices from that point to the output, they're not, the gain square will be much lower, and then those noises will be again divided by the gain square. So the message is the input stages or the stages which are in the beginning, those transistors will contribute more towards the noise compared to the transistors which are close to the output. And therefore, those transistors must be carefully designed with respect to the noise. Now, a very quick, because I don't know how much time do I have. I think it's already 1:15. So maybe I'll very quickly go through the last set of slides. That is just to give you a snapshot of how you can design a single stage op-amp having a cascode. I think it will not take more than 10 to 10 minutes. Do I have the time to continue? Hello?
Uh,
Shall
sir,
I?
Yeah, actual time is over, but 5 to 10 minutes, I think it will be good if you conclude with single stage op amp, because it will
I think,
have,
I
have a
think,
completion of topic. Yeah.
I think it will be, it will help
Yeah.
that way,
Yeah.
because I tried to convey as much as I can throughout the whole
Yeah.
landscape. All right.
Yeah.
So so
Yes.
if I have how to design a very simple single stage op amp, which is like I have already given you the idea. Now, what I have done is I have assumed very simple specification. The output swing is 3 volt. The power dissipation is 10 milliwatt, and the voltage gain which I need is around 2000. And then, of course, in a given 0.25 micron technology that I'm having, so what are the different steps that is involved? First of all, as I told you already, the power is most important. The power budget is 10 milliwatt, and that power budget will decide the current levels. Now, the most important current is the current flowing through this branch, and we ensure that this current should be large because they are the most important. They'll set the agenda. So what I have done is, out of 10 milliwatts, this I9, the current, this is the main current sink for this. I have allocated 3 milliamperes. We can do all sort of allocation. 3 milliampere current is for this, because for 10 milliwatts, my budget will be around 3.33 milliampere current, because the supply voltage is 2.5 volt for my design, because the technology is 0.25 micron. So for 0.25 micron technology, the supply voltage is around 2.5 volts. So I can afford around this 3.33 milliampere for a 10 milliwatt budget. So for that, what I have done is I have set I9, the main current, because is around 3 milliampere, and then in the current mirror, the reference I have assumed IMB1 will be around 330 microampere. So in all, if I combine these two currents, the overall power budget will be around 10 million. So what happens is I have set the current through my IM9 transistor, and you all know that the two branches should have the same current. So the two branches now will carry around 1.5 milliampere each, 1.5 milliampere and 1.5 milliampere. Now what really happens is the output swing is 3 volt. You know that in a differential, the output swing is twice the swing in a single branch. So if I take the differential swing is 3 volts, so the single branch swing on Vx or on Vy will be half of it, and therefore each node X and Y must swing just by 1.5 volt to get the required swing of 3 volt. That is my specification. So first of all, I have set the current in the two branches based on the power budget. Then from the output swing, what I'll do is, based on the output swing, I'll find out the values of the overdrive voltage for M1, M3, M5, and M7. Now, I know the output swing will be around 1.5 volts. In the next slide, it will be clear. So it means that I would have to find out what is the maximum value of Vx I can have. The maximum value of Vx that I can have will be equal to what is the drop across this, and the drop across this, to ensure that this transistor must be in saturation, it should be just equal to the overdrive, which is VGS minus VT. VDS must be equal to VGS minus VT. So the VDS I can set equal to just the overdrive. So the overdrive voltage for this I'll set, which is VGS minus VT. I have set, this is like Vx max will be, the maximum voltage will be that for proper operations, all these 4 transistors must operate in saturation. And therefore, their VDS should be at least VGS minus VT. And therefore, the Vx max that I can have is, it's the VDD minus the overdrive of 7 and minus the overdrive of 5. Why? Because at least this overdrive will ensure that transistor M5 and M7 will be at the edge of saturation. Now, what is, so the Vx max can't go above this, otherwise the transistor M5 and M7 will come out of saturation. Now, similarly, we can calculate Vx min. Vx min will be the overdrive of 3, 1, and 9, VOD3, VOD1, and VOD9. And therefore, the output swing will be Vx max minus Vx min. And this we already have, it's 1.5 volt. Now, if I use this expression, you put these two equations here, what I'll end up in, the summation of all the VODs must be equal to 1.5 volts. Now, what we have, now we have to decide. Now, this transistor M9 should carry the maximum current for the power budget, and therefore, it should have the highest value of VOD. So what I have done is, why it should have higher value of VOD? Because it's carrying the largest current, and therefore to keep its W by L minimum, I should allocate more VOD to M9 compared to others because it is carrying twice the current. So let's assume that I have set VOD9 equal to 0.5 volts. Then how much is available for the other VODs? Only 1 volt will be available because this summation of all the VODs must be equal to 1.5. 0.5 is already allocated to M9. So VOD1 plus VOD3 plus VOD5 plus VOD7 will be just equal to 1 volt. Now, how to allocate? Do they have same VODs? No. Why not? Because you know that the PMOS transistor will be having a lower mobility. If the PMOS transistors will be having a lower mobility, it means that its VOD should be large, otherwise its WIL should be large. Mobility, the ID is mobility times WIL into the VOD. And therefore, if the VOD of the PMOS transistor is large compared to the NMOS, since its mobility is lower, we can keep the WIL in check. And therefore, we have to allocate more VODs to the PMOS compared to the NMOS. And hence, the VOD for the PMOS, VOD7 and VOD5, I have kept at 300 millivolts. That will make it 600 millivolt. The remaining 400 millivolt I have divided in terms of the NMOS transistors M1 and M3. So what I have done is I have set the overdrives from the output swing specification. I have extracted the overdrives of all the five transistors. And for the other branches, it's absolutely identical. So I have just taken one branch. Now the VOD is available. The VGS minus VT is available. The drain current is available for all the transistors. And therefore, we can always compute the WIL ratios. And what we have done is, based on this, the WIL ratios have to be computed. Now we have computed WIL ratios. They are coming out to be this WIL for one. There's also weird values are coming, but I think it all depends on the design values. We shouldn't bother about it. WIL9, we are getting this. But then this will satisfy the power dissipation, the swing, and the supply voltage specifications. What about the gain? We require the gain of around 2000 for this design. But then if we use the formula of the gain for this differential amplifier, what we are getting based on the WIL ratios that we have, if we apply the formula, then we are getting, unfortunately, the gain is only 1.141. So the gain specs are not met. So what we can do? The problem is, till now, what we have done is we have used minimum channel length transistors to keep the size minimum. So if the gain specs are not met, the easiest way is increase the channel length. Now, increase the channel length of which transistors? Increase the channel length of the NMOS transistors or increase the channel length of the PMOS cluster. Now, this will be debatable. This will come from the bandwidth specifications also. And what people have found in this circuit, if you increase the channel length of the NMOS transistors, the bandwidth will be more drastically affected compared to the channel length of the PMOS transistors. And this will come handy from the frequency response analysis, capacitance analysis. So what has been done is, in order to realize the gain specifications, what can be done is increase the channel length of M3, M1 transistor, and let's say the M4 and M2, rather than using minimum channel length of 0.5 micron, 0.25 micron, 0.5 micron in this case, we can use a channel length of, let's say, 1 micron, and then recompute the gain by keeping all the other values. Of course, so the channel length goes up, the channel width will also have to go up. And then if we do that, what we have found that if I increase non-minimum channel length higher than the minimum, of course, the area will go up, the W will go up proportionally, but then the gain will go up to 4,000. So by doing that, we are able now to get the gain of 4,000 by increasing the channel length of all the NMOS transistors. Now we have leverage. We can redesign it till we achieve the required gain of 2,000 by choosing just the by tweaking again. We do another iteration, and then we can reset the overdrive voltages so that we can get the required value of gain by a lower WIL ratio. And this is, let's say, an iterative process. What the message is, get the specifications first, try to satisfy some of the specifications, and some of the other specifications will not be met, and then go on redesigning it till all these specs are met. So if you choose L is equal to this twice the minimum, then of course the gain specification will be met. And then now you have leverage. You're getting much higher gain. So you can, rather than using double the channel, then you can do some other overdrive strategy, like assigning some different overdrives to different transistors, and get even better results compared to what you are getting here. What do I now conclude? Because I think I don't have the time. Analog design requires thorough understanding the device physics along with proper approximation of device models. Remember, you have to replace each transistor by its approximate models so that you can do hand calculations. You can find out by inspection which transistors will contribute towards the dominant pole. Remember, the EDA tools are just the verification of the approximators that you are getting through hand calculation. Layouting is very important to understand the parasitics. And you should be able to identify the building blocks of complex design for ease of analysis. And you all know that it's getting tougher at the nanoscale because of the variability of the MOS transistors and reduced supply voltage. And of course, with digital, it's become even more worse. Thank you very much. If you have any questions, then I can help you.
Sir, in chat box, I think there is one question.
Yes. What is that question?
I reference, to generate I reference.
Okay, I think because of the paucity of time, yeah, I think there is a reference for me. I reference, you have to go through the band gap reference. Band gap reference is a very standard technique for generating a current, or let's say a reference voltage first, which is immune to this temperature variations, which is immune to supply voltage variations. How they have made it immune to temperature variations is they have generated, like, let's say KT by Q, which is like a Boltzmann list, like KT by Q is like, it has a positive temperature coefficient. And you know that VBE, it has got a negative temperature coefficient. So they have used in this circuit very intelligently VBE plus VT term so as to eliminate the dependence on temperature by just one having a positive temperature coefficient, another having a negative temperature coefficient. So you can generate a V reference where you have one term which has a positive temperature coefficient, another term which has a negative temperature coefficient, and then similarly, I think they have eliminated the supply voltage variations also. So you have to go through the design of the band gap reference. I was not having the time. It's there in most of the books. So band gap reference is a separate topic, how to generate the band gap reference where the supply voltage is independent of temperature and supply voltage variation.
So one more question is there. Let me read.
Yes.
Gain W by L 124 transistors 1250,
Yes.
and W by L is 1111. How these are obtained?
No, actually, all right. Yeah. The problem is the time. You see, I think because this will take. Okay, all right. You know, I think I'll. Right. All right. All right. Yeah. Now, how these are obtained? Look, the current is set, ID. The current is known. And what is the overdrive? The overdrive is like VGS minus VT is known. So the current is known. You know the expression, and the transistors are in saturation. So you can go back and use the same expression. The drain current is known. The overdrive of the transistor is known. And then all the other parameters are known. You can just compute the W by L ratios. For that, I'll just go back to the MOS models. I'll go back to the MOS models. I think that will make things clear, because I'm sorry, I've just kept it to the minimum so as to. All right. So I'll go to the expression in saturation so that will help. Okay. Let's hope I'm here. All right. Look at this expression. Forget about this lambda VDS term because we keep it simple for hand calculation. This is the overdrive voltage, VGS minus VT. This we have set for the different transistors so that they operate at the edge of. So VDS we have set equal to VGS minus VT. So V overdrive we have decided from the output swing. From the output swing we have decided the overdrive. The drain current we have already decided from the power budget. Now what is left in this? Forget about this lambda. This Kn dash is known from the technology. You can compute the W/L ratios. So because once the drain current is known and the overdrive you have set, you can compute the W/L ratios. That's what I have done. I have set the overdrive and now I can compute the W/L ratios because the transistors are operating in saturation using this expression. So I think now if I go back to this from the, remember here, from the power budget, I have set the current of this transistor, and IM9 is carrying 3 milliamperes. So now this branch will carry half of it, 1.5 milliamperes. So drain current is known. I have set the overdrive depending on the output swing specification. So output swing specification, I have set the overdrive of the different transistors. From the overdrive of the different transistors, I can, overdrive means VGS minus VT. So VGS minus VT I have set for the different transistors. The drain current is known. I can find out the W/L ratios. Is that clear now?
Yes, yes. As mentioned, yes.
All right. Any other question?
No, it's okay, sir.
All right. Thank you very much.
Yeah.
Thank you for inviting me and bearing me for so long.
It's okay, sir. Yes, sir. Participants wait for 5 minutes, huh? Like, you know.
Thank you, sir, for discussing the basics of analog CMOS design. You have highlighted the key points that how design is indifferent from analysis and how the parameters like gain, bandwidth, voltage swing, input-output impedance, power noise, linearity should be made to circuit specification. You have given a very important message that hand calculations are very much important, while EDA tools is only a way we can verify our circuit. If you are to understand the circuit, we have to perform hand calculations. I'm sure that your session will be benefited by a lot of participants present here. Thank you, sir, for accepting our invitation. Kindly accept a virtual memento as a token of thanks.
Thank you very
Thank
much.
you.
Thank you, Anand. Thank you.
Thank you, sir. Thanks a lot. And we will again have a session in the next FDP.
Yeah. Hopefully,
Yeah.
I'll be in less pain in that session. Yeah. Okay. Thank you very much.
Thank you, sir. Thanks a lot. Thank you very much. So, participants, just one or two instructions from my side. Please join on time because it's an analog design, and if you miss the starting, it is very obvious that you won't understand what's happening next. Next point is every day there is going to be an assessment. So there are around 60% participants common coming from the STTP1. So they know that every day morning there will be a quiz. It is on Moodle platform. Your Moodle logins are already being created. If you if you are not able to log in into Moodle, please let me know by the evening. In the evening, you check because our system admin is still creating for few of the candidates. So if you're not able to log in by the evening time in the Moodle, please let me know. But assessment is compulsory. You must face the assessment. Whatever is the result of assessment is that secondary, but you must face the assessment. So assessment has to be there on the Moodle platform. Every day morning we will have a quiz from 8 o'clock morning to 10:30. During this time it will be open. Half an hour as per your schedule, you can appear for the quiz. One attempt will be there. Okay. So please do that. And the attendance and the feedback form, as usual, will be circulated in the evening slot. So today evening we have Dr. Naushad Alam. He will be taking us through SPI simulations. So during that time, attendance and feedback form, it is both combined together, will be circulated. So please fill that also. Okay. And please be interactive during the sessions. That's it. So thank you very much. We'll meet in the evening at 5 o'clock. Okay. Thanks a lot. So now you can leave the meeting. I'll close it.